Максим заходил.
А?
Максим заходил, отметил.
Ну, вроде. Там все то же самое примерно.
Вот этот только 20-й, который.
Ластовире который?
Нет, который я забыл.
А, Меркин?
Меркин, да.
А Ластовире это будет, не будет?
Ластовире, да, он сказал, что я, говорит, его видел.
А?
Видел, говорит, его, да, он будет.
То есть он будет?
У меня еще сомнения по поводу кого-то есть. То ли этого, то ли... Типа он, говорит, крепит, и хрен знает, будет он выступать или не будет. Но если что, говорит, мы найдем, кто за август. Что-то такое, ну, в общем.
Ага, ну то есть первые 4 пока у нас есть.
Вроде да.
Ага.
Да, 4 стопудово есть, да.
Все, хорошо.
И он еще вот этого что-то не отметил. Меркина тоже стопудово не будет.
Меркина, да. Точно не будет, да?
Угу.
Все, хорошо.
Ему что-то там командировку не платили, ну, короче, какие-то заморочки. Я, говорит, его раскручивал на онлайн доклад, он что-то, говорит, не раскрутился. А, еще вот тут будет 2 доклада сразу. А, слушай, так они не наши.
Да, это один мой, это оба мои.
Это вот вы, да?
Да, и Рожков, и этот, и предыдущий, это было как там, Терентьев или кто? Терентьев, ага.
А почему ты этих двух отметил, смотри?
Что пишет?
Один доклад, 15 минут.
Они объединяются, что ли?
Вот, видимо, так.
Пермский завод машиностроителей, Бабушкин. Национальный. Короче, надо будет у него спросить. Доброе утро. У нас все в порядке.
Я ничего не трогал, ничего не делал, ничего не смотрел.
Ну, предполагается, что да. Если что, мы свистнем, хорошо? Спасибо, Андрей. Так.
Что я не сообразил, что они у нас с тобой разные.
Это. Водички схожу быстро.
Ладно, да не спеши, мне кажется, еще там собираются.
Ну, что-то вон начали чесаться.
Шел вообще ни хера никого нет.
А?
Я говорю, шел, когда пришел, вообще никого обычно не было.
А в зале-то вообще кто-нибудь есть? Ну, сейчас что там 1,5 человека, я зашла в фойе-то стоят.
Мне кажется, много и не будет. Вчера, наверное, мне кажется, еще чисто так нагнали. Есть только эти все москвичи.
Угу. Ладно, что, будем по факту, как говорится.
Наши я все равно не видим.
Ну.
Это вроде там.
Ну. Раз. Ага.
Даже грызей вообще нет.
Да? Нам-то что, блин, опять так и пропадает картинка. Я даже все не дочитала. Вчера. Сегодня почитать, посидеть будет. Слушай, а у нас по программе там обед какой-нибудь есть или только все кофе-брейки?
Перерыв?
Да,
Мне это не обозначает обед, но это понимаю, что они, если напишут обед, то все будут ложками стоять.
Где час перерыв?
Вот перерыв.
15-20. А, все-таки есть, да? Хорошо.
Может, я что переиграю, но часто.
Час, то есть есть. Я просто там по времени, я уже это не смотрела, честно говоря. Я смотрела, поскольку доклады. Ладно, окей, спасибочки. Так, сейчас кто у нас? Нет, сейчас начинают другие дядьки. Кто там? А, Фортуна. Фортуна, их два доклада у него. Да ладно, что?
Дураков с Кубани.
С Кубани, да? Ага. О, ничего себе его занесло-то.
Не, он онлайн делал.
А с Кубани-то где он там? Моторин, Елисеева, Меркин, Рожков, Рушкин, Семенов, Шуков. Все-таки будет, да, он? То мы тогда убираем. Ай, да ладно, короче, фиг уже с ним, не буду ничего искать. Блин, слушай, картинка, по-моему, чаще мигать стала. Что у них тут опять? Good morning to all the conference participants. Let's start our second day of our conference. And we will start with the reports. Sergey Fortuna at the topic forming additive products from a heat-resistant alloy with given structure. Dear colleagues, I will make 2 reports. This is the first one, and then I'll have the second one. So for me and for my postgraduate, tomorrow he will protect his thesis. So the topic, one topic flows into the second one. The topic has already been announced. I must note that this investigation was supported by the Russian fund. I will allow myself only one popular slide about the additive technologies. On the left picture, it is shown that one and the same bracket is made by additional technology and by additive technology. The amount of source material and the amount of material remained after finishing. So it's just like for the students. To the right is the picture from the NASA side. If to go by link, we will find the publication. This was printed for 90 days. The 3D model of the nozzle of the Russian engine. The height is about 176 meters, if I remember correctly. And the diameter is about 1 meter. It was printed off the powder. Additive technologies, though local, but are metallurgical technologies. So in printing the products, the characteristic structure is formed, which we can see here in the picture. This is made of titanium alloy of VT6, printed a vertical wall, about 30 centimeters height. So the grain structure can be seen. And the length of the grains reaches tens of millimeters. nanometers. So it's not very good always because there are a lot of technologies. Yesterday we had the report about the forging proposed. So in our institute we also have some kind of similar methods to in order to obtain equiaxed structure. But directional structure is not always bad. In this case, this is good. If the material is here high temperature alloy and the temperature is a turbine blade, we can see here the evolution. So previously the blades had equiaxed structure. We can see here, then the directional structure was invented. And now nobody is surprised with monocrystalline structure, which are being grown. So we decided to make our investigation. Well, monocrystalline we cannot reach, but directional structure can be reached by our methods. The material of the study is high temperature alloy GS32. It is intended for directional crystallization because it contains rhenium. And apart from rhenium, it has another 8 alloying elements. It's a complicated alloy material. This material, or this table shows the charge material for the bar, and then the printed material. So this is one of the bar of the product printed by us and made a chemical analysis at half height. And also according to the regulatory documentation, these are the specifications according to which we choose them. We use the material. Here we must note that the content of aluminium in printed materials is lowered. This is a fusible material which is in vacuum processing. It evaporates. But our structural investigation of the elements showed that it can be replaced very good by tungsten. Here you can see the tungsten content that in the product higher than in the feedstock. So we can assume that the properties, the high temperature properties of such products will be lowered. But when we printed it, we didn't know it. And I will tell about it a little later. Again, the set of studies that we performed in our institute shows that the strong additive technology allows to produce some product, maybe some shape, maybe a vertical wall. The main parameters in the technology are accelerating voltage, beam current, and working table speed. So all these characteristics are bound with the heat input, with the ratio of heat input. It was also established that to print a product, we must control this heat input. And the simplest method to control it is to use beam current. It turned out that the beam current should be reduced as the product is printed. And through approximation, we understood that this reduction shown here has exponential form. It depends on the material. It doesn't depend on the material. It was confirmed also on aluminum alloys, nickel alloys, steel, and other materials. Here we can see the actual values of 2 products. For this heat input change is shown with height or with the number of layers. The same characteristics are shown for the other 4 products of this work. We describe 6 products. Here I can say that this teeth is for the printing for multidirectional printing as against the other products. Here we had the printing in different directions, and that's why we received such zigzag shape of the curve. This table summarizes the values of heat input and the constituents of heat input expressed in beam current Here we show the initial and final values in the course of printing. And also we can see that the product obtained by mode 3, the working speed the working speed table was lower. The notes indicate that the method of heat removal, it's quite clear that heat removal in all cases was made through the substrate of the product itself, or which was fixed on a working table, but we had some nuances. In some cases, we just suppressed slightly this heat removal through heat conductivity. This is for the case of the product number 2. We did the gap in between the substrate and the working table, and this worsened the heat removal. These are 6 products. These are the diagrams, which was what was implemented. Product 2 was distinct with the gap, which is shown here. Product 3, as I already told you, had the heat input was lower due to double speed of working table. This was multi-directional printing. And the product number 5 we obtained through isolation of working table. We put in the heater, and before starting the process, the substrate was heated up to 400 degrees, and this was maintained through printing of the whole product. And here it was specified the beam current reduction down to 85. And the last diagram is around the product. The reflecting screen was placed. Here we dealt with the radiation constituent of heat removal. So it was in vacuum chamber, and the heat removal can be in 2 ways: heat conductivity through substrate and isotropic from the melt bath through the chamber walls. So we compensated it slightly with a mirror screen. Here we can see the process itself, printing of the wall. This is the accelerated shooting. The printing took about half an hour, 40 layers, height of 46 millimeters. We specified such parameters. The wall height was to be 50 millimeters, width 11, and well, we didn't maintain the specified parameters in the technology. And one more thing I should note is the peculiarity of additive manufacturing from high temperature alloys is non-deformable because they have intermetallite strengthening, and we made the bars. We developed the feeder with the box for 48 bars and with the cross section of 12 millimeters and the length of 146 millimeters, and this allowed us to print the products of 84 millimeters high. Today we have implemented triple height printing, but we have to stop the process, recharge the box, and continue printing. So here we can see all 6 products. This slide, here we see BD is building direction, the direction of the product forming, and ST scanning trajectory. This is what I have already told you about. In product 4 is multi-directional printing. So the peculiarity of the morphology of the product we can see. We did measurements, and we can state that products 1, 5, and 6 had the least deviations of the specified parameters. The other products are either surface melted, generally surface melted. But it's interesting that product 3 where we remove the heat input through increasing the working table speed at half height, we can see that it's surface melted in this way. It was unexpected, but it can be explained quite clearly. And So our task was the response to the material response to environmental factors. Here we see the diagram of cutting out the specimens for a structural examination. This is this side, what we are looking at. These are macro sections prepared from the product 1 and 2. These are just macro photos. We can see that the structure is directional from the substrate till the last but one layer. These are colonies of dendrites. We can see they grew from the substrate till the last but one layer, and this is characteristic for all the products. We can see that dendrite colonies are inclined towards the building direction. So, and these angles were measured as well as one of the structural characteristics. And these are other 4 products. Macrostructure is shown. The product for which we reduce the heat input, we can see that after reduced, the directional structure is lost. So it turns out that even if speed is higher, the layer is printed faster. But in this process, the such kind of heat is accumulated that cannot be effectively removed through a substrate. And the prevailing becomes the radiation constituent, and this results in aqueous structures formed. So here it's everything is clear, and this is exact directional structure. And the other products are just very nice structure. These were macro examination. Here is micro examination. Here we can see raster microscopic images. It turns out that in the middle of the product, closer to the substrate, here we can see the contrast colonies of dendrites. They are all parallel to each other. And in the top portion, the dendrites they grow horizontally. When printing the next layer, it remelts, and all the rest have the same structure. So complete reproduction of the previous layers, and more refined structure is here. Means that colonies of dendrites consist of dendrites themselves. These are axes of dendrites. So dendrite structures have the characteristic which is called the distance between the dendrite axes. This is the analog of the grain size for aqueaxed structures. We measured this characteristic. Here we can see for product number 5. These are the results. And also we measured the angles. The table summarizes the measurements of these structural characteristics. The average inclination value is as half height of the product relative to the printing direction, and the average size between the dendrite axis of the first order. We can see from here that the least distance is for product number 1, and with the angle of 24 degrees. And I would like to outline the product number 5. We can see that at the least angle, vertical, and with a moderate increase of the grain size. Because we can understand what's the process, because we removed more heat. So these are the conclusions made by us. In which product the least inclination exists. But if we go to some real products and print them, and our products that we printed are comparable to the real products, we can specify the model at some certain angle and print at this angle. So these are the first ways for discussion and experiments. But we selected not that one product, but the first one with the least distance between dendrites. So now I switch to the next report. And these are mechanical properties of the material of additive products of high temperature alloy at room and elevated temperatures. The same authors within the same grant. They were printed 7 walls according to mode 1. We can see the general presentation of it. And from it, they were cut out cylinders along the building direction. Some of these cylinders were heat treated, and from all of them, the tensile specimens were manufactured. Here we can see 4 hot tests. This table summarizes everything. At room temperature, the tests were carried out according to GOST 1497, and we can see the heat treatment modes. For these are standard for GS32 alloys, and the measured and average values. At elevated temperature of 900 degrees, the GOST was 9651, and the same some were tested, some were not tested. These are very representative diagrams. I will comment on them. On the left, the colder color shows the room temperature, and to the right, with the at the elevated temperature. A total of 4 tests were made for each kind, and 2 parallel for in heat-treated and non-heat treated condition. I should say that the specimens number 3 and 4, they have total coincidence. These specimens for mechanical tests were made of different walls, but looks like for us it was unexpected that they look like just very alike. These are heat treated, and they have a very nice elongation of 16%. Even in monocrystalline condition, we can reach 15%. This is for GS32U improved. And these characteristics are for the first and second. These are non-heat treated. We can see that elongation is much smaller, and tensile strength and yield strength are quite high. So with the black arrows that are shown, the yield strength of sigma 0.2 and tensile strength for the same alloy GS32, which is improved alloy. This is temperature information. It turns out that tensile strength is a little smaller, about 5% less, but the yield strength is 8% higher. Looks like that for the products for which it can be used, this is more preferable, because these should work till reaching the yield strength. At elevated temperature of 900 degrees, for us it was also unexpected that heat-treated products the material has worse characteristics than in monocrystalline condition, and in non-heat-treated conditions the characteristics are quite comparable. The elongation is quite significant, average value of 8%. And for the GS6, GS32 alloys, 800, 900 degrees, this range is not very convenient because they lose ductility of the material. But here we can almost reach by tensile strength and yield strength the characteristics, and by yield strength we exceed. And this is in monocrystalline condition, and these are very interesting and unexpected results for us. But frankly speaking, here are the conclusions. We first saw it in mechanical tests and then saw in structural examination, in electronic microscopic examination. And we checked phase composition, and it turned out that printed products require no additional heat treatment, which is done at all other methods: casting, co-directed crystallization. It turned out that these repeated heating of the material in the printing process are the module. So this goes beyond these reports, but we have these results, we have obtained them, and it's realized without the harmful brittle phases, and this heat treatment is homogenizing, and all the elements that should be formed, they are seated where they should. So, and is this is not a creep test at elevated temperature, but it turns out that these are quite satisfactory. And creep test is in progress just at the present time. And it turned out that now at the creep test of 100 hours, the creep exceeds 360 megapascals, but the real value, I cannot tell you more exactly. This is worse than with monocrystalline material, but nevertheless, this is due to lack of aluminum is partly compensated, and the second reason that we took the specimens not along the line but along the building direction, and this can introduce these changes. Okay, dear colleagues, this is all I had to tell you. Let's thank Mr. Valeri for a very interesting report. Do you have any questions? One moment, microphone, please. These are macro photos. This is just a setting. These are shadows, the tints. There are a lot of factors on which the tint influences. It does not reflect the true state. So probably somewhere pickling was more, somewhere less. You see the surface, it gives tints. And at different focus, you should make pictures. They are almost same. So, but when we see in a raster electronic microscope, they are also the same. Some other questions, please? Could you please tell us, in the first report, could you return the table with the properties? You told that evaporation of aluminum is very high. But what about the chromium? In initial alloy, the content is 5%. And I didn't see the chromium content in the deposited metal. Okay, let's check. This is the table of chemistry. Let's check chromium. This is chromium. This is in deposited metal. So here the chromium content is less. Okay, thank you very much. It's clear now because it was not very clear previously. And another question. Didn't you think that it should be compensated the chromium with initial charge? Yes, of course, we have such kind of ideas in Novosibirsk. They manufactured in Polytechnical University the line of producing wire or some other products. Yes, this task exists and is put. And also on the same VT6 printing, aluminium evaporates very perfectly. So this work, yes, is in progress. We specified this and we showed this, and that it should be compensated and the content should be increased. And then to make some products and continue printing. Any questions? Mr. Sergey, thank you very much for the report. The question is as follows. You said that you were going to print the blades of GS32. No, we're not going to print the blades. This is not for our conditions. I just told that the dimensions are comparable to the ready-made products. Of course, there is no aerodynamic profile. It's just a plane. But probably, of course, we have some ideas to add something to make some real products. Any other questions? So again, let me please one question. Could you please show the slide with the diagram of the result? What do you think why specimen 3 and 4 after heat treatment have such different angle of the portion, like Young's modulus is different 2 times? How can this be explained? Let's say heat treatment here was harmful because these harmful phases are precipitated, and again the specimens were cut out. Were not cut out along the dendrite, but along the building direction, and these the output of these phases was accidental. It turns out, and they didn't want specimen somewhere that there's a less quantity of this. Here, the quantity is higher. GOST requires that we make 2 tests. Well, again, was not this problem of entrapping? No. It's surprising that the grips, they stood this test. Well, it happens sometimes with the tensile specimens that the grips, they get deformed. Well, yes, but here the grips were side and these were threaded, and both at room temperature and at elevated temperature. Again, then the second question, what do you think? How the inclination angle, the crystalline inclination angle, can be controlled? Can it be reduced somehow? Well, frankly speaking, this is beyond the report, but as the information I can tell you, in our team, it was shown on other materials that not only printing, but heat input can be also controlled. We can, due to this control, we can receive a strictly vertical growth. It was shown on other alloys. When we printed the same products, the heat input was different, and we received equiaxiality and also multidirectionality. But the printing was multidirectional. It can be arranged multidirectional printing, but with our material, this is more complicated. Heat input shall be reduced, and we moved to the area where we decided the cracking would occur. So we have some kind of range to receive a directional structure with the condition of flawless. So first of all, without cracks. With ecoaxial technology, these are some peculiarities of the work. Okay, thank you very much. Your report was very interesting.
Yes, hello. Now the next speaker is Alexey Goncharov from Moscow Power Engineering Institute. The topic of his report is investigation of electron beam parameters and technological complexes for EBW by light radiation from the drift space. Good day, dear colleagues. I'm not going to repeat the topic of my report. Here you can see it on the slide. My presentation will be dedicated to determining the parameters or characteristics of the electron beams used in the technology, first of all, in the welding technology. A few words about well-known mechanisms of deep welding. When the channel in the material is formed under the action of the beam, or the beam directly affects the vertical wall. In this case, the beam is characterized by the tool, by the set of certain parameters: beam diameter, convergence, angle, all our beams are conical. And power energy, some average power energy, some average power density, so it's indicated with the red color here. But when we initiate the process, the physical parameters are basically unknown to us. We know the beam current, the welding speed, and the focusing current, which characterizes the position in the focal plane against the welding thickness. And it's well known that this parameter is determinative one, and it influences the welding shape. And so you can see here the shapes, and with different focusing currents, the shapes can vary from parallel walls to conical ones with overfocus welding, these ones. This weld when the focal plane is too high. And there is a problem how to combine the existing technological parameters with those parameters of the physical model which will determine the fusion. So therefore, there is a task to diagnose the beam, and here you can see quite a wide range of classifications of different techniques, different methods. They can be split into contact and contactless, and among contact ones we can also distinguish direct or probe methods, when the probe, basically the metallic one, is inserted into the beam, and according to the probe signal we can register some characteristics. And also indirect methods among which we can see the radiation meters, different radiations, and we can talk about of quite simple in the approach. It's photodiagnostics, is the registration of visible radiation emerging due to the drift of the beam. Just a brief overview of the methods, diagnostics methods in different application spheres and technological spheres. Basically, probe methods are used. Sorry. Here we can see the references on the bottom, in the bottom. And among the methods in acceleration techniques, there are contactless methods, contact methods, indirect methods by visible radiation, by beam ions. But there is no finished, completed number of works in photodiagnostics are not existing, at least we couldn't find them. Just a few words about the formation, the scheme of beam formation in classically used electron guns, triode, electrostatic lens. With first electrostatic lens and the second magnetic lens. As a result, in the electrostatic lens, the crossover is formed, which cannot be converged into the point due to several reasons. It has limited dimensions, the trajectories cross under different angles, and so there is some crossover in the narrowest flow of electrons, which is called crossover. And the magnetic lens actually sends this crossover to the transversion area, and it works with small magnification. And in the treatment zone for welding tasks, we have the beam with the cross section around 1 millimeter. It can be several dozens kilowatts with the power of it. And even here in this model, we can see some peculiarities of distributing the density, the power density. So this power density can be characterized by the density of these trajectories. There are just a few, but nevertheless, in the divergent after the crossover, there are such areas with low density, with low power density, then unlimited, practically unlimited in the space. But when we're talking about the limited beam, so it has physical boundaries, this flow, and the task, as we put it to ourselves, to define the numerical determination of the boundaries of this flow. So the investigations were made on 2 plants, actually more, but here we have the results only on 2, OL 144 and LR 15E. So they are equipped with similar guns. The only difference in this plant is that this system has, so there are 2 levels of deflection for parallel transfer and double beam refraction. So the experiment scheme looks like this. So we made the shooting at the distance for about 1 meter from the camera illuminator to absorb. So there was a target to absorb the beam energy and block the light from the target to the diaphragm. And from the transport area, the luminous beam was registered with the help of photo camera. Just a few words about what we see. We see not the electrons, but the result of electron interaction with residual gases in the chamber. But those pressures at which the diagnostics was carried out allow us, assuming that some plasma processes, ionization processes with a sufficient degree are not here. We see the result of interaction of electron with the atom, either by elastic dissipation or relaxation. Based on this scheme and this method, what is formed on the plane of the detector is basically some integral projection along y-axis with some space of distribution of density, of current density, or power density. This is also some kind of remark that should be done. So the technique of processing the images, what parameters did we want to consider? So its focus and distance, so the coordinate of section with minimum size of the beam. So this is the minimal diameter of the beam, and convergence angle. So it makes sense to define it at distance, because in this overdraw, so this angle always changes, and in this section it will 0, and also the divergence angle depending on what area we are going just to register. So the processing scheme is demonstrated here after the plant. So after we get the image, so then it was a RAW file, so we converted it into TIFF format. Then we selected the colored image, converted it into monochromic ones. So, and from 3 colors, we selected the best one for the signal to be indicated. Then we got the matrix. Afterwards, it was mathematically processed, and as a result, we got the characteristics which were declared. And if we registered the current of the beam, so based on certain algorithm,
we can move to the if not to the profile of the beam, but to this integral profile, and to calculate the mean density of the power. And this is not a complicated task. So the problem was to define the boundaries on the image, because those images which we obtained, they had some blurred boundaries, and the reason for these blurred boundaries is that the illuminator glass, so we see the image from made with the old glass and with the new one, and you can see the differences in boundaries. But anyway, so if we even the glass is good, anyway, the profile we register cannot be used directly to define the size or position of the boundaries. So we can visually, with the help of some rulers, we can draw the lines with the help of the rulers, but it won't be the mathematically verified operation, so therefore it will be the subjective in most of the cases. And the task was actually to get rid of this subjectivity. If try to use the differential operators like Sobel algorithms or Kenny algorithm to define the boundaries, we are facing the problem that those operators reveal only more boundaries than the existing ones, because the flow has two boundaries, right and left. And what we see inside as a boundary is actually some peculiarity of the internal structure of the beam. It's not basically the physical boundary. Moreover, those algorithms don't allow us revealing these characteristics in all the sections. If we use the a priori information that we have two boundaries on the image, then we can consequently process from top to bottom with some step these integral profiles. With the help of the integral wavelet transform, we can get the points of the right and left borders, and then when we put it onto the graph, due to the difference of these coordinates, we can calculate the diameter and plot such a graph of diameter change on the distance from the gun Z, and calculate the section with the minimum size of the beam. And just to confirm it, we carried out such a shooting of some reference sample, which can be accurately measured with experimental methods. So these are two photos with through the glass and without the glass, and you can see how optical elements contribute the roots when we collect the image. And with the help of the proposed technique, we managed to determine the position of boundaries both on the image without glass and on the glass through the window, through the glass. And this blurring of boundaries didn't influence it. On defining the position of the boundary, so the relative error on the reference sample was 0.3%, and its relative values is 33 microns. So the examples of the diagnostics on the plant UL144. So the beam current is 240 milliamperes. So the focusing current, and so the mistake was made actually by the error. So it's the blue graph. It's is the diameter, and the red one, it's numerical differentiation. And on the right, you see the profile of the beam. this integral profile. And for another plant, so the current of the beam is 5 milliamperes, so the error is higher, about 9%, and so the minimum diameter is 214 microns. We checked the influence of vacuum on the results of the diagnostics, and we managed to get it at two different pressures, but it was dynamic vacuum because during pumping out it changes in these plants, and it's very difficult just to maintain it at the same level. And so there's just a 10 in -5 increment and 10 -3 increment, so the difference in diameters and the distances are identical of the same modes of the beam. It's 50 milliamperes. Besides these methods of applying to investigate the internal structure of the beam can be seen, so we can see the peculiarities of this method inside the boundaries, if they are available. In case of the rimmings, you can see it's a circular trajectory with different radii. You see here the minimum in the center, so the rimming in straight line, and here in the circumference you can see 3 points. So it's the projection as we look at this figure, from this side, and we see in this projection that these peaks are at different distances. But finally it was possible just to converge all this to some approximative dependencies. The minimum diameter on the focusing current approached the linear function quite well, approximated the linear function quite well. So you can see all these parameters here for both plants, and the distance, the focusing distance here. So it was used here. You can see the results also, and as a parameter which allowed comparing, for example, these two guns, we can propose such a parameter as sensitivity of the focusing distance, how many milliamperes of the focusing current are necessary to change the focus position by 1 millimeter. But this is in the assumption of the linear dependence, but actually it's a quadratic one. But this parameter is more qualitative, but at least it's seen well that it differs more than twice for both guns. To verify the results, to verify the measured diameters, we measured them. Video,
да, где мы
you see here
померили
the shots from
по видео
different videos where
диаметр
using
пучка
this
при
video
сварке
we
и
measured the beam
непосредственно при
diameter
сварке.
during welding,
И оказалось, что он
and
довольно
it turned out
хорошо
that
совпал с тем, что было
it
измерено по
coincided
фотографии.
quite well with those
Ну
measured
и
by
надо, конечно,
photos, and
иметь в виду,
it's
что
necessary to take into
вот эти
consideration
вот
that
диаметры, они
these
содержат большую
diameters
ошибку, то есть это
contain
очень приблизительные
huge
значения.
error, so these are quite approximate
Дальше
values.
мы
Then we
как бы сопоставили
compared
вот результаты
the
диагностики
diagnostics
с тем
results
проплавлением, которое было
with the
получено,
fusion, fusing
получили
penetration which we got, and we
зависимость
got the
глубины,
dependence
ширины
of the depth
проплавления,
and
нижний график,
width of
от
fusion.
параметра F, это
From F
заглубление фокуса
parameter,
от
it's the
лицевой
deepening of the
поверхности
focus from the
детали.
face plane of the
То есть
surface
мы
of the
теперь
part.
точно уже знаем
So we
положение
now
плоскости
definitely
фокусировки, да,
know the
и
position of focusing
вот
plane,
оказалось,
and it
что
turned out that
при сварке
when
плита
welding,
была 56
the plate was
миллиметров,
56
глубина у нас
millimeters, the
максимальная получилась
depth
около
was
52 миллиметров,
about 52 millimeters, the maximum
ток,
one,
по-моему,
and the
240
current about
или
two,
чуть меньше, то
240
максимальная
or
глубина
maybe a bit
проплавления
less, and the
при
maximum
минимальной ширине,
maximum
да, то есть вот,
penetration depth
режим наиболее
with this
глубокого
mode,
проплавления
the
достигался
deepest
при
mode was
размещении
reached
плоскости фокусировки
when the
вот
plane
прям
was
даже за
positioned
немножко границей
just after the
плиты.
boundary of the plate a bit.
Отклонение
So
и в
the
ту, и в другую сторону, естественно,
deflection was
приводило к уменьшению
in
глубины
one of that
проплавления.
direction,
Вот
so
эти
it
точки, это
decreased
не
the
одна точка, это
penetration depth. So
осреднение по
this is
5
not one point.
сечениям.
So it's we compared using 5
Плите
sections on the
было
plate.
сделано 5 сечений, то
Five
есть
five
корневая
sections
пила,
were made on
которая,
the
возможно,
plate,
присутствовала, она вот в этих числах как бы
and
осреднена, можно
and
сказать.
it's averaged here.
Ну и подводя
And
итог,
making the conclusion,
вот те
those
параметры пучка, которые
parameters of the
мы
beam which we
определили, мы нанесли также
found,
такую диаграмму
we
координатов
just
мощности,
entered
плотность
them into the
мощности. Я вот не
diagram,
сказал про среднюю
defining the
плотность мощности, но мы
density,
ее тоже
the
определяли,
average power density. We also
вычисляя
found
через
it,
диаметр
calculating through the
и
diameter
известные
and known
энергетические
power
характеристики через ток
characteristics,
ускоряющие.
current,
Вот,
accelerated
и
current,
в этих
and
координатах
those
вот эти пуски
coordinates,
оказались
those
ну,
guns
где-то как раз в области
were in the region
технологического
of
применения,
technological
называется
application,
SRAM.
what we say welding.
Ну, здесь
And
представлены
here
некоторые выводы,
you
я
see some
позволю их не
conclusions.
зачитывать.
I'm not going to read them. Thank you for your attention. If you have any questions, you are welcome.
Благодарим за доклад.
Thank you for your presentation.
Я думаю,
I
работа
think
будет интересной
the
специалистам,
work will
которые
be interesting for
занимаются достаточно
specialists
сложными
dealing
вопросами.
with big depths of welding. So
Спасибо
please,
за интересный
questions.
доклад.
Thank you for your report, interesting presentation. If I got it correctly, you looked at
Приличных токах в районе 250 миллиампер
high
смотрели
currents and you
плоскости,
checked the parallel
на которые
planes
помещались вы.
on which you
Как
got the welds. How
как сварочная ванна не засвечивала видеоизображение? Вот в чем вопрос.
how the welding
Видеоизображение?
how
Да,
the welding
видеоизображение,
bath
которое вы
Ну
didn't
вот в данном
light
случае, вот,
the image, the
к
video
сожалению,
image.
вот не удалось
Unfortunately,
показать, да,
I
там
couldn't
просто
show you
минуты.
this video,
Мы
so
снимали
it's
строго
turned
с
upside down. Yeah, and actually we
плоскость,
shot it
вернее
in
так,
the
чтобы вот ось оптического объектива совпадала с
for the
лицевой
axis of
поверхностью
optical
плиты.
objective to
Ну
coincide with
и
the
настройкой
plate surface
параметров
and the adjustments of the
фотосъемки. И
parameters of
еще
the photo
используется
shooting,
фильтр
and also we use the
поляризационный.
polarization filter.
то есть вы за счет поляризации решали?
So you solved it
Ну да,
using
да,
polarization,
чуть-чуть
yeah.
пришлось там отрегулировать.
So it
Это
was necessary
из
to adjust
съемки.
it
При
a bit,
фотосъемке мы
but during
не
the photo,
использовали
taking photos, we didn't
ни
use
фильтров, ничего.
any filters.
Еще вопрос, да.
Another question.
А вот не совсем понятно.
It's not
Вот
quite
ваш
clear
метод измерения
your
плотности,
measuring
да?
methods of
А как вы
the
фокус
density
определяете?
measuring methods.
Метод
How did you
положения
find the focus, the position of the
Мы,
focus with your method?
скорее даже в
We,
первую очередь
well,
определяем
first of all, we
геометрические
found the
параметры, в
geometry,
том числе
geometric
положение
parameters, including the
фокуса,
focus
и во
position,
вторую очередь
and secondly, the
плотность
density,
энергии.
power density.
Значит, вот положение,
The
то
position.
есть наша задача
So
была
our task was
определить
to find the
координату границ
the
пучка на
coordinates of the
изображении.
beam
Если
boundaries
мы
on the
знаем
image. If we
координату
know the
границ,
coordinates of
то
the
мы
boundaries,
тривиальными операциями,
so
вот я
using
сейчас
trivial
покажу вот здесь,
operators,
наверное,
I can show it
видно.
here on the slides for
Вот
you
эти
to
красные
see. So
линии, да,
these red
это
lines,
в результате вот работы
as a
алгоритма,
result
да,
of
выявленные
the
координаты
algorithm,
границ.
so
А дальше
we
уже
defined
эту
the
тривиально
coordinates of the
обработать,
boundaries, and afterwards
для
they were
каждого сечения
processed
получить
for each section and to get
номер
the
строки на
number of the
изображении,
line
да, в которой
on the
диаметр
image
занимал.
in which the diameter is
Если я
taken,
правильно понял вопрос.
if I understood your question correctly.
А скажите еще,
And please
пожалуйста,
also
вот
tell us
верификация
the
произведенных
verification
измерений,
of
никто
this
не готов
measurement.
Ну,
Did you
верификация
make verification
Ну, вот вы меряете
of the
сколько
methods?
там
So you
миллиметров,
measure
сколько
just some
миллиметров,
millimeters,
и
or
вы еще другим методом
and maybe it's
померили.
necessary to use another
Я
method to
понял ваш
measure
вопрос,
it.
спасибо.
I got your
Да,
question, but
ну вот непосредственно на пучках
So
мы не
we
измеряли
didn't
другим
measure,
методом.
we
Именно
didn't use
эти
other
пучки,
methods
это
on the
ну,
beams, on
довольно
these
сложно.
beams, because it's
Во-вторых, вот
quite
этих вот
complicated.
зондовых
And
устройств
also
для
using these
зондовых измерений, как и серийно,
probes.
ну, мне неизвестно.
So I don't know where to get them just
Мы
manufactured serially. So yeah, so actually it was difficult
проводили
to
такую
get the
верификацию
probes.
вот на
We
эталонном
carried out
объекте, да,
such
то есть мы
verification
вот
of the
прям в камере
reference
размещали
object. We
такой вот
put it inside the chamber,
светящийся стеклянный
such a
стержень,
glowing glass
диаметр
rod
которого мы можем померить,
with
ну,
the diameter of
вот
which can be
10-28
measured.
миллиметров
So
электронов,
it's
как мы его
like
померили, да, а потом
10,
по
28
его
millimeters,
фотографии
and then using its
определили
image, the
вот этим
photo,
методом
we
тот же самый диаметр, вот он здесь
we
внизу
defined
приведен. Вот
the
мы считаем, что это
parameters,
доказательство
and we considered it
того, что
to be
мы
the proof that
определяем правильно
we
положение границы.
find the position of the
Причем это было
boundaries
сделано
correctly,
как в
and it was
условиях,
made both
когда у нас нету
under the conditions when
вот этой
we
вот
didn't have
засветки, скажем так, границы от стекла, да, как вот здесь, так и в условиях, когда есть
from the
стекло и
glass,
есть вот
and
эта вот
also in the photos, in the
засветка в виде
images
границы,
with the
которая мешает,
glass.
собственно, по таким профилям определить, где
So sometimes the glass can just handicap the correct definition of the boundaries. Thank you for your presentation. There is a question: what cathodes did you use? Because it depends on. So it was tungsten, tantalum, or which one? Yeah. Thank you for your question. So our research was on the hexabarite.
Косвенного накала, да.
So indirect glowing.
Таблетка 4,7,
So
диаметр
tablet
имитирующий
4 by
поверхности
7, like the surface of 4 millimeters. So I think my report was very interesting for you. Do you have any other questions? And can I also ask you a question? How is it possible to evaluate the accuracy of the coordinates by axis Z?
Хороший вопрос, спасибо.
So it's a good
Да,
question,
действительно,
and actually
сферическая операция есть, это уже
there is spherical aberration,
все-таки
and
вещи более
so these things are
высокого порядка, скажем так,
say of
ошибки,
higher
да,
rank, so
которые
such
возникают. И
errors
это, кстати, даже
which we
видно,
are
если проверил
facing.
эти
And
картинки,
this is seen, but
по
I
этим
actually didn't
картинкам,
show
да,
you
когда
this on the picture.
мы определяем
But even if
диаметр
you take these
на
pictures when they
цилиндрическом
find the
стержне,
diameter
мы
of the
на самом деле
cylindrical
получаем
rod,
там небольшую
we get
различие
some
диаметра
deviation
вверху и
of
в
the
центре камеры, это
diameters
как раз
on
сферическая
top and
операция объектива.
in the middle. So it's the objective
Но это можно вот, опять же, по калибровке, которую
spherical
можно получить вот таких измерений, можно
aberration
учесть.
of the
Но хочу
photo
сказать, что
camera.
если в абсолютных
But if you
цифрах
take the
вот от
absolute
160
numbers,
или 190 миллиметров, которые мы
from
измеряем, это
160
будут
millimeters,
ну,
so
десятые
they
доли
are
миллиметра.
like tenths of
Скорее даже там
millimeters,
1-2,
maybe 1-2 tenths of the millimeter. Thank you.
Ну, если
If
вопросов больше
there are
нет,
no more
благодарим
questions,
докладчикам.
we'll say thank you
И
to our
следующий доклад у
speaker.
нас делает
And the next
Артем Юрьевич
presentation
Марченков.
is made by Artyom Marchenkov from Moscow Power Engineering Institute.
Да, уважаемые коллеги, добрый
Dear
день.
colleagues, good day.
Я представляю Московский энергетический институт,
I
лабораторию
represent
механико-технологических
Moscow Power
испытаний
Engineering
и оперативной
Institute.
диагностики материалов. Вот, и сегодня
And
доклад
today,
будет посвящен
my report will be
остаточным
dedicated to residual stresses in welded structures. And so this topic is quite new for our laboratory. And I'll start with the works carried out before that.
В работе пойдет речь об остаточных
I'll talk about residual stresses of the first order, like macro stresses emerging at the level of possible wells.
Размером характерным, наверное, это миллиметры.
If you're talking about some certain dimensions, so these are millimeters or just We are not talking about microstress. We are not going to talk about microstresses. And so the reason for the emergence are clear for everyone. How we carried out our investigations before. A couple of years ago, there was such a work when the hardness method was used to determine. So just to remove these residual stresses from the sample, just to free the wells from the stress partially and measure hardness and got some statistics. And it was measured before and after cutting, checking and evaluating the differences, and we evaluated the residual stress by the hardness, difference in hardness. So here are some photos on tungsten alloy at different welding speeds, arc methods. Welding were also used, and briefly the results were as follows. And actually they were just, we saw changes from 3 to 5% in hardness, and it was seen that residual stresses influence the hardness. And so these changes by the height of the welds, and you can see here are the differences before cutting and after cutting, and it decreases. And a few years ago, it was decided to use another method for measuring. So the diagram is made in the and here we see this the kinetics of changes of the shifting depending on the load. Most important, the hardness which we get, so it will consider also both elastic properties of the material. So our laboratory has been dealing with this for quite a while, and we use them both for distribution of mechanical properties in welding connections. And the previous conference, the head of the laboratory reported about the steel 30 HGSR, not only hardness but also plasticity of the welds themselves, just to predict the area of decomposition, of destruction, and so on. And also we managed to define the critical temperature in this region, the distribution of this temperature by the weld areas. And at the moment, as we are dealing with the refractory materials testing, the task now is to learn how to measure it at certain the temperatures of 500 degrees and higher. So in theory it's quite simple, and if there are compressive stresses, this is the diagram indentation diagram, it changes in one direction, and if there are compressive stresses, so it changes in another way. So we have two actual stress. So the character of changes of the curves, indentation depth is the same. And here everything depends on the ratio of main low stresses, and the diagram will also deviate either to the right or to the left, so it's given here. In our literature there are methods used to see the difference in hardness and to check and to measure the residual stresses. If you try to use this as appropriate to welds, so the technique will be as follows approximately. So it's necessary to find somewhere the first point here, the zone of the residual stresses, then to check the hardness and the sample, and then using the suggested algorithm and the difference in hardness, try to find the residual stress. So we use the following algorithm. So we use the steel 10 Na2 MFA, and so as the reference sample free from residual stresses, we checked the hardness in this, cutting it and
оставили
removing
здесь
from the residual stresses, and
такую
then
небольшую полосу размером
we
шириной
left
примерно,
here the
ну, чуть
band,
более 2
small
миллиметров.
one,
И
about 2
определили так
millimeters
называемое эталонное значение
wide,
твердости.
and then we
Затем
got this reference
на
hardness.
неосвобожденном шве, да, можно
Then
сказать, на второй половинке
on the
этого
second
шва,
half of this
уже
weld,
исследовали значение твердости,
we
можно сказать, в
investigated
зажатом состоянии,
the
то есть в состоянии после
the
сварки.
hardness
Ну
parameters
вот
after
здесь для
welding.
сравнения
And
приведены
if you
две
compare
диаграммы,
it, so
которые,
you
в
see
общем-то,
two
наглядно
diagrams,
показывают,
and they
как это
visually demonstrate
отличие
the
выглядит. Да? То есть,
differences,
на
how they
диаграмме
look
мы
like.
видим
On the
по
diagram, you
линии
see
разгрузки, то есть положение линии
the
разгрузки
loading
отличается
line,
и
and they
характер
differ,
кривой
the
напряжения
positions of
тоже
them, and
отличается. И,
curve,
соответственно,
loading
полученные
curves,
значения
those are
твердости также
also
будут
different.
отличны.
And so therefore the hardness
Вот.
parameters
Затем
obtained are also
можно
different.
по
Then it's
разнице значений
possible,
твердости
using
определить
this difference in hardnesses,
остаточное
to
напряжение.
find the
Если,
residual
условно говоря, нам
stress.
повезло, да, то
If
есть
we are
для
lucky,
стали
for example,
такого
for
класса, да,
steel of
значит,
this
у нас
grade,
есть проведены данные
we
по
have, you can see this,
изменению
these
внутренних остаточных
parameters,
напряжений в зависимости от разности
residual
значений
stresses
твердости.
changes
Если
with different
такого,
hardness
если у
values,
вас
and
какой-то там,
if you
условно говоря,
don't
другой
have,
материал, да,
or
то
if you have
есть,
other
то
material,
есть не стали перилитного класса,
not
да, то
the
тогда,
perlite
конечно,
steels, but some other
задача стоит
steels, so
в
then
предварительном установлении
the
такой
task will be
зависимости
to
с
find
использованием
this
специальных приспособлений.
dependence using
Ну,
special
здесь
fixtures.
можно отметить, что делается это
And
один
here
раз,
you can
и
see that
затем
this
можно
is done only once,
использовать, по крайней
and
мере, для
then
одного типа
this can be
сформации.
used for just at least one
Ну, в
type of
общем,
weld joints,
результаты,
welding joints. So the
результаты измерения
results,
показали
measured results
следующее,
demonstrated the
что
following.
в сварном шве,
So in the weld,
полученном ушной сваркой, да,
in the
присутствует
joint, with the
достаточно
help
высокие
of
остаточные напряжения, и
electron beam
верифицировали
welding,
мы эти
so we
напряжения
have
с помощью
stress,
рентгеновской дифрактометрии.
residual
Вот,
stresses, and they
упрощенно
were just
можно
found
посчитать
with help of
тоже
X-ray
суммарное поверхностное
diffractometry,
остаточное
and you can
напряжение,
see the surface
поскольку
residual
изначально
stress,
рентгеновская
because it
дифрактометрия дает
usually
нам
the
вот эти вот два
diffractometry
напряжения,
gives
да,
us these two
ну, главные
stresses,
напряжения, возникающие
let's say main
на
stresses
площадке,
emerging at
на которой
this
производится
area
измерение.
where we take the
Ну, что могу
measurements.
сказать по
What can I
результатам, да, то
say
есть
just
тут
based on
сравниваем
the
с даже
results?
два
If you
столбца,
compare
да,
these
это
two
вот
columns
инструментальное
here,
индентирование и
it's tool
рентгеновская
indentation
дифрактометрия,
and
то, конечно, можно
X-ray
увидеть, что
diffractometry.
значения, конечно,
You can see
отличаются,
that the values
отличия даже,
differ.
можно сказать, там, и в 1,5 раза
It can
есть,
be like
однако, в общем-то,
1.5 times,
что
but
радует,
we can say
это
that
порядок, да,
the
одинаков,
order is the
знак
same at
напряжения
least,
одинаков,
the
ну
sign
и
of the stresses is
так или
the
иначе
same,
можно,
and
наверное, сделать
we
вывод,
can
что
say, we can
для
conclude that
предварительного
for
такого, да, анализа,
preliminary
не применяя
analysis,
сложных методов
not applying
измерения остаточных
complicated
напряжений,
methods,
как
the
та
measurement
же
of
самая
residual stresses
дифрактометрия,
as
еще более тонкий
diffractometry
способ,
and
электронная микроскопия.
finer
Вот этим
electron
способом
microscopy,
инструментального
for
индентирования,
example,
конечно,
finer
можно,
methods.
ну, мы, по крайней мере, предлагаем
We at
пользоваться
least
на,
just
в том числе, и
advise you to use
швах,
these
полученных
methods
специальной ушной сваркой.
also just on
Ну,
the
сразу что можно
joints
сказать, да, метод,
obtained
конечно,
with the help of
не всесильный, да, не
electron beam
всемогущий.
welding.
Нужно
So
понимать,
it's, you know,
что
that it's
неоднородность, если
necessary the
присутствует неоднородность металла
homogeneity,
шва, конечно, это
the
будет,
non-uniformity
или
of the weld if
структурная
it's
неоднородность,
available,
или отдельные
structural
зоны какие-то,
non-uniformity or in
структурная
separate
неоднородность. Конечно,
areas.
применение
So of
этого
course
метода
this
в
method,
этом случае будет, безусловно, ограничен.
this
Ну, а так, в
method's
общем,
application will
такое у
be
нас
limited in this case.
предварительное исследование
So this is our
выполнено.
preliminary research.
Есть направление, куда двигаться
So
в этом
we
плане.
see
Значит,
where to
это
go
исследование как
further
раз-таки швов с высокой степенью однородности.
to weld
Вот.
the
Ну и
to
некоторые
measure the welds
совершенствования
with the high
методики определения твердости, что
homogeneity
участвует не только
degree.
твердость, но и параметры
Not
деформационного
use not
упрощения.
only the hardness
На
as a
этом
main
все.
parameter and
Спасибо
other
за
parameters as
внимание.
well. So this is all. Thank you for your attention. Thank you for your presentation, for your report. So the topic of the report is quite complicated and discussable. Yeah, and actually waiting for your questions.
Короче,
Артем Ильич, очень интересно, конечно.
Yeah, it's very
Как
interesting. It's an interesting report how the diameter influences the accuracy of your measurements.
Влияет, Дмитрий Карпович.
It
Влияет
influences, yeah,
достаточно
it
сильно.
does, and quite
Значит, вот на этом
quite
примере,
sufficiently. And on this example,
значит,
which I demonstrated to you,
2,5 миллиметра,
so
надо
2.5
понимать,
millimeters, it's
что
necessary to understand
около миллиметра от
about
размера
1
отпечатка,
millimeter from the
поэтому,
print
конечно, значение напряжения
size,
получится
and
достаточно
actually,
сильным.
yeah, so the residual
Не
stress
стал
will have
приводить
some kind of averaged value.
исследования, значит, сейчас уже перешли на 0,2
I didn't demonstrate all the works which we are dealing with now, and we now use smaller diameters, but actually we didn't have
Скажите, пожалуйста,
verified results. And your recommendations, what weld shape is supposed to be to minimize the residual stress?
Да, вопрос интересный,
It's an
спасибо.
interesting question. Thank you.
Посоветуемся с коллегами, сварщиками.
So we'll discuss it with our colleagues, the welders.
Параллельные стенки первое, что приходит.
Parallel walls first comes to mind.
Я думаю, тут это конфигурация изделия.
Or maybe configuration of the
Конфигурация
product,
материала, да.
configuration of the material,
От жесткости.
Жесткости.
rigidity.
Вопрос.
Question?
Спасибо за доклад. Достаточно
Thank you for your report.
провокационный вопрос.
Provocative
Прозвучало
question.
название доклада «Оперативный контроль».
You called it operative
И
control.
отсюда непонятно, в чем
And
его
it's not clear
оперативность, как мы будем
why do you call it
контролировать
operative,
напряжение
how
в реальных изделиях,
to measure
которые сварены.
the residual stresses in real products. No, it's not provocative,
Да,
it's
пока,
a
наверное, до
good
оперативности
question.
здесь
Yeah, we are
далековато.
not talking, we are too far from
Единственное,
operative
что, да,
methods.
может быть, хорошо, что
But maybe
в
it's
любом
good
случае,
that anyway
будем так говорить, подготовка
we say that the preparation
образца даже,
of the
если мы говорим
sample,
про подготовку
if you talk
микрошрифта,
about the
она,
preparation
конечно, существенно
of the
проще, чем
sample,
по
it's
рентгеновскому
much
спектру,
easier if
проще.
you're talking about X-ray
Вот. И
diffractometry,
второй
it's
момент,
easier.
если
And the second
мы говорим про
thing, if
однотипные
you talk
сварные
about
соединения, то при
the
наличии
same
талона
types of
кондукционной
welds,
зависимости, которая
and
безусловно
if you
нужна,
have such a
они
mode
делаются
of
один
this
раз, а
dependence,
дальше
so
мы
they're
можем,
done once,
условно говоря, по
and then
накатанной
we can
использовать
just use them
для
already
однотипных сварных
for the
соединений,
same
которые
type
получены
of
там.
welds.
А тогда, пока
And then,
контроль
yeah, so
является
actually
образцовым, то, в
it's
принципе, в любом
like a
случае
reference
требует
control, basically it
подготовки.
needs
Перейти
preparation,
на готовое изделие без разрезки пока не
and
представляется
without
возможным.
cutting it's impossible to be carried
Да, вот
out.
вопрос девушка хочет задать несколько.
So a lady wants to ask a question.
Спасибо за доклад.
Thank you for your report.
Вопрос не такой.
And I have a
Если
question.
вы говорите, там делается
If you
один образец,
talk
или
about,
вы
yeah, let's
всё-таки
make
делаете
one
несколько
sample.
образцов
Yeah,
в одном шве, чтобы
you make
проверить,
only one sample
как
or
отличаются
several
параметры
ones on one well
образца?
just to
Просто вы
check
сами говорите,
the
что
difference in
индивидуального носителя
parameters.
с реперным у вас разница в 1,5 раза
And you
была.
say you said that there was the difference. Yeah, so actually, did you do it
Я
parallel
понял.
on
Честно
several
говоря,
specimens?
статистики пока
Yeah,
очень мало.
frankly,
Вот.
I'm missing the statistics. It's
Вчера
not
тоже с
sufficient.
коллегами
And
обсуждали.
yesterday we discussed it with the
Вопрос
colleagues,
был тот же,
and the
что
question
будет,
was the
если я возьму
same:
там,
what happens if I
грубо
take
говоря, там, у меня есть один образец
roughly,
там
yeah, I have one
сваренный,
sample,
второй
welded
образец,
one,
сколько
second one,
мне для
and
каждого эталона нужно?
is it
Нет,
necessary for each
пока
reference
предполагаем,
sample to
что
make
нет,
another
эталон должен
specimen?
быть
Yeah, so we
один.
think that there's supposed to
А
be
по
one
поводу того,
reference
что разница
only,
с реперным
and
образцом в
we are
1,5
talking
раза, то
about the
реперный
difference in
образец, он
samples, so the
был
reference sample, yeah, so
освобожден от
actually
внутренних
it was
повреждений
freed from
из-за этого
internal
разницы. То есть,
stresses, so therefore it was such a
ну и
big
для
difference.
понимания,
And for you to understand, so
верифицировали по
we
дифрактометрии,
verified by using
и
diffractometry, and
дифрактометрию как раз делали
diffractometry
на,
was
можно
carried
сказать,
out, let's say,
разрезали напополам,
we
да,
cut
то
it
есть, и с
by
одной стороны
halves,
сделали
and on
дифрактометрию,
one
с другой
side
стороны
the
сделали
diffractometry was made,
индентированную.
and
Вот, поэтому,
indentation was made on the other
сами видите,
side.
некоторая
And as
разница
you
есть,
see,
конечно,
there is some difference
между
between
значениями. С чем это связано,
both
с
samples.
методическими вещами или
It's
с тем,
connected
что
with
там
some
на
maybe
расстоянии 1
methodological
миллиметра
things,
поменялось
or the
напряжение, ну, наверное, пока
distance
тоже трудно сказать.
changed. So, yeah, so we cannot say it
Да.
exactly
Ну и
right now.
дальше,
Thank
насколько
you.
это будет потом применимо. То есть
And how
чисто
applicable
вот
it
это
will
внедрение,
be,
то есть вот это вся
the
разработка
introduction
шаблонов,
ways.
можно ли это будет потом дальше
Can it be
все-таки
used
как-то
further
привести к тому, чтобы это применять?
in practice?
Понятно, вопрос
Yeah, it's clear. I
понимаю.
understand your
Ну,
question,
наверное, все-таки
but
голословно не хочется
I
говорить.
don't
Наверное,
want
все-таки
just to
нужна нам
say
некоторая
without any
статистика.
proofs. Actually,
Пока это, можно сказать,
first necessary
демоверсия.
just to
Пока
get some
демоверсия.
statistics.
Да.
Okay, thank you.
Спасибо за вопрос.
Thank you for your questions. We are just already, we already been delayed. I also wanted to ask you, but yeah, yes, thank you for your presentation.
И следующий доклад у нас делает Моторин Максим Павлович.
Mr. Maxim Maturin from TETA.
Добрый день, коллеги. Я чуть-чуть подвину.
I'm greeting you, dear colleagues.
Добрый день, коллеги. Мой доклад
Once again, I'm greeting
называется
you.
электронно-лучевая
My
пушка
report is
мощностью
called
150
Electron Beam
киловатт
Gun,
для
150
сладких,
kilowatt
других
for welding, melting, and other
операций.
process operations under vacuum.
Электронно-лучевая пушка была изготовлена по
Electron beam gun
заказу
was manufactured by the order of Chepetsk Mechanical Plant,
энергокомплекса
as part of an energy complex for welding and surface melting.
Упрощенная конструкция
Simplified
электронно-лучевой
design of
пушки
electron beam gun
представлена
is shown here.
на рисунке.
The picture.
Скажем так, вид ее
стандартно, ничем
It
особо
looks
она не отличается.
standard.
То
It
есть это
doesn't have any
верхний корпус,
peculiarities in appearance.
катодный узел,
Cathode assembly,
средний корпус,
middle
анод,
housing, anode,
вольфрамовая спираль,
tungsten helix,
катод,
cathode,
фокусирующая верхняя катушка,
focusing upper coil,
система напуска газа,
gas puffing system,
камера промежуточного давления,
intermediate pressure chamber,
турбомолекулярный насос для
turbomolecular pump
камеры промежуточного
for
давления,
intermediate pressure chamber,
нижняя фокусирующая система и
lower
отклоняющая
focusing
система.
system and deflecting system.
Так, здесь представлено
Here
более
it's shown in more
подробно.
detail.
Источников электронов
The
является
electron source
танталовый
is a tantalum
катод. После
cathode
накала
of indirect heating.
принцип
The principle
состоит в следующем. То
is
есть у
as
нас
follows.
вольфрамовая спираль
We have
прямонатальная,
tungsten
которая
helix of
течет
direct heating, and
между
in which
вольфрамовой
current is flowing
спиралью
in between the tungsten
и
helix and
танталовым катодом прикладывается
tantalum
напряжение,
cathode
какое
as
силовое.
voltage
За
is
счет этого
applied.
электроны
This
имитируют,
results in emitting the electrodes
ускоряются
and accelerating the electrodes
нагретой
from
вольфрамовой
the
спиралью.
heated
За счет этого
tungsten
нагревает
helix.
танталовый катод,
It hits tantalum
что
cathode,
впоследствии его разогревает,
and then it heats up further.
и за счет ускоряющего напряжения,
And with
происходит у
accelerating
нас
voltage,
возникает у нас электронный пучок.
electron beam appears.
Формирование электронного пучка.
Electron beam is generated,
Формирование электронного пучка выполнено на основе
is made
диода
on
Пирса.
the base of
В чем оно
Pierce
заключается?
diode.
Это
The principle
сферическая
is
рабочая
this is a spherical working
поверхность катода,
surface of the cathode,
определенная форма
defined
динельта
by the shape
и анода
of the
позволяет получать
anode, and it allows
сходящийся
to
электронный пучок,
get
который потом
converging beam,
впоследствии
which is subsequently
подфокусируется верхней.
is also focused by the upper coil.
Здесь представлена
Here we can see
конструкция,
the
то
design,
есть внешний вид
the appearance
электронно-лучевой
of the
пушки с ее
electron
основными
beam
параметрами.
gun with its main
Ускоряющее
parameters:
напряжение от 10
accelerating
до
voltage of 10 to
35
35
киловольт,
kilovolts,
диапазон тока луча
beam
до
current
5
range of
ампер,
0 up to
максимальная мощность,
5
которую
amperes,
можно получить
maximum power
с
obtained
электронной пушки 150 киловатт.
is 150
Конструкция
kilowatt,
пушки позволяет
and the gun design allows
получать
to
угол отклонения
obtain the
электронного пучка
deflection angle for electron beam of plus minus 45
Все
degrees.
остальные параметры,
All other
скажем так,
parameters
они уже
are
посредственные.
just standard.
Так, дальше представлены
Here we
уже
can see
технологические задачи,
the process
которые
tasks
выполняются
which are
данной
made
электронной
by
пушкой.
this
То
electron
есть
beam gun. These are
это брикеты
briquettes
циркониевые,
of zirconium,
которые для переплава
which for melting are welded together
электронным лучом.
by electron beam,
Технологические параметры
and
здесь
the
указаны, то
process
есть
parameters
это
are given
ускоряющее
here.
напряжение до
This is
35
accelerating voltage of up to
киловольт.
35
И ток
kilovolts,
луча
beam current of
до
up to
1,2 ампера.
0.2 amperes,
Также еще
up to
одно из
1.2 amperes, I'm sorry.
применений это
Once again, application,
сварка
it is
циркониевых слитков,
welding of zirconium ingots,
циркониево-титановых
zirconium and
сплавов.
titanium alloys.
Ускоряющее напряжение
Accelerating
и ток
voltage
луча такой же, как
are the
и
same,
для
and beam
сварки
current are the
циркониевых
same as
брикетов.
for zirconium briquettes.
И, скажем так, изюминка
And
это
the
оплавление слитка.
peculiarity
То есть для оплавления
is
слитка
surface
используется
melting,
ускоряющее
surface
напряжение
melting of
до
ingots,
35
accelerating
киловольт,
voltage of the
с рабочим
up to
током
35
от
kilovolts is used
2,2
for
ампер
with beam
до
current of
3,5 ампер.
2.2 up to
Такой
3.5
разброс
amperes
тока
used.
связан с
This
давлением,
current
которое
consumption is due to the pressure
в рабочей камере, то есть
which exists in the
в камере,
working
в которой
chamber,
происходит оплавление.
in the chamber where surface melting goes on.
Луч при этом
Here the beam
отклоняется на
is
23
deflected
сантиметра,
23
глубина
centimeters.
ванного
The
расплава при
melt
этом
bath
до
depth
20
is
миллиметров.
down to
То
20
есть
millimeters.
здесь
That is,
представлены
Here we
сам
can
супер
see
оплавленный,
the surface melted ingot,
ширина
the
шва.
width of the weld,
И в дальнейшем этот слиток
and further this ingot
разрезается на две
is
части.
cut into
И
two parts.
также здесь представлено,
And here we can also see
что с ним в дальнейшем происходит, то есть после
what
покупки.
happens with this ingot afterwards.
Также,
So
поскольку электронно-лучевая
since the
пушка
electron beam
не
gun
может работать
cannot work
без
without
высоковольтного
high
источника
voltage source,
питания, который также на 150 киловатт
which is also
шкаф управления,
designated, which is
поэтому
also
также
intended
здесь
for 150
представлен.
kilowatt, and
Еще одним
power supply cabinet is also shown here. And
элементом у нас является
another
пульт управления.
element here is operator's panel. And
В заключение
conclusion
я хотел
is,
бы сказать, что
I would like to say, to conclude, that
ТЭТа в дальнейшем планирует
TETA is planning for the future
продолжать разработки
to continue
и
developments
сделать серийное изготовление мощных энергокомплексов
and to start batch production of powerful energy complexes of 300 and 600
для
kilowatts
таких применений, как рафинирование,
for such
плавка,
applications
и в
as
том числе-
refinery,
и в том
melting,
числе получение
and also
термозащитных покрытий.
production of
Спасибо за внимание.
thermal protective coatings.
Поблагодарим
Thank you very much.
докладчика.
Let's thank our speaker.
Прошу вопросы.
Please questions if you have. Thank you very much for your report. One moment, please.
Спасибо за интересный доклад.
Thank you very much
У
for your
меня
interesting
вопрос.
report. I have a
Вот у вас там
question.
была
You had,
схема пушки, да,
you had the diagram of the gun.
линзы у вас.
You had, yes, I understood there are two focusing lenses in it.
И когда вы там вот говорили о технологии,
When you told
ширина
about the
пучка 230
technology, the beam
миллиметров. Это в
width of
режиме развертки. Там
230 millimeters. This is a scanning mode. Yes.
Вот какова рабочее расстояние
And
между пушкой и сведенным пучком?
What is the operating distance between the gun and converged beam after the second lens? Yes, I got your point. If we talk about the ingots for surface melting,
Если мы говорим про
if we talk about the
слитки для
ingots
оплавления,
for surface
то
melting,
рабочее расстояние
the operating distance is up to 350 millimeters.
Вторая линза, она тоже увеличивается.
That is, the second lens also is also enlarging.
линза, она нужна для
No, the upper lens is needed
транспортировки
to
электронного
transport the
пучка в области
electron
дрейфа без
beam
потерь.
in the drift area without any loss. And the second lens, focusing lens, is required for us to receive the required density. Yes, I understand. But in between these lenses, there is a crossover.
Расстояние от кроссовера до второй линзы,
Distance from the crossover to the second lens is less than the distance from the second lens to the image. And it looks like the second lens is enlarging. So the distance is 350 millimeters.
Или вот где кроссовер
Or
находится между линзами?
could you please show me where is the crossover between the lenses? Where it converges and then diverges.
Нет, я имею в виду кроссовер не... Да, вот здесь.
Yes, here, correct. Crossover here is a graphite jar. So means the crossover is here in intermediate chamber. In the intermediate chamber is needed that we have a high deviant beam, and depending on the process application, we puff gas into it, and the gas is puffed for us to have ion focusing. For volumetric special charge, and also for creating the pressure drop, and additionally protect the elements of the cathode assembly, tantalum cathode helix, and to increase the service life. Thank you. And in the preliminary chamber, is there any window? Yes, there is an inspection, of course. In the pre-chamber,
Девятый.
Number
Девятый.
9.
Это камера промежуточного давления.
Yes, in the intermediate pressure chamber.
Там стоит свинцовое стекло.
Yes, there is a
То есть,
LED glass
помимо того,
installed,
что на графитовый стакан установлен
and
датчик
also
температуры,
onto the graphite jar there is a temperature
также
sensor installed,
свинцовое стекло для
and
того,
also the
чтобы
LED glass
оператор мог
for the operator to be able
воочию наблюдать.
to look
Спасибо.
through the inspection glass and observe. Thank you.
Вопрос.
Yes, I have a
Спасибо за
question.
интересный доклад.
Thank you very much for the
Такой простой
interesting
вопрос.
report.
Почему
I
вы
have a
ограничили
simple
входящее
question.
напряжение 35 киловольт, казалось бы, для повышения
Why are
мощности
you
пучка
restricted
можно
by the
поднимать
accelerating
напряжение
voltage
до
of 35
повышения
kilovolts?
Также достаточно просто.
It's very simple.
Потому что
We did this
разработка была
because the
связана с
development
модернизацией
was
уже готовой
related to
установки.
upgrading
В связи
already
с
existing
этим
plant, and due to this,
камера
the chamber
не позволяла
did not
использовать
allow using
электронные пучки
electron
большей
beams
энергии,
of a
потому что
higher
не
energy
защита.
because there was no protection.
Скажите, пожалуйста, а
Could you
какого
please
диаметра
tell us
катод
what's the
используется?
diameter of the cathode used?
Конкретно в этой конструкции
In this
диаметр катода 18
design,
миллиметров.
the cathode diameter is 18 millimeters, and the hole diameter is
около 3 миллиметров.
about 3 millimeters. Thank you.
Еще вопрос?
Any other questions?
Нет.
No more questions.
Позвольте мне тоже тогда вопрос задать.
Let me
Я
ask a
правильно
question
понимаю,
myself. Am I right in
дальнейшее
thinking that
повышение мощности вы планируете за счет ускоряющего напряжения?
that
так,
further
все-таки?
increase of
Вот
power
300
you plan due to accelerating
киловатт,
voltage
600
of
дифференса,
300,
за счет
600
чего
kilowatts?
мощность дальше?
What's the basis of increasing
Есть
the
в планах,
power?
что если на 300
We have
киловатт
in
это
plans
увеличение тока,
that for 300 kilowatts this is increase of the
если мы
current,
говорим о 600
and
киловаттах,
for
то это
600
и
kilowatts
увеличение напряжения,
this
и
is also
увеличение
increase of
тока.
the voltage and of the current.
Чтобы повысить мощность в 2 раза,
And
насколько
to
увеличится у
duplicate the
вас
power,
размер катода?
what will be the increase
Есть
in the
уже
cathode
какая-то
size?
наработка или это
Do you
пока
have any works in this area?
Увеличить мощность вы имеете в виду до 600
Increase
киловатт?
the power, you mean up to 600 kilowatts?
Конкретно этой задачу мы еще не просчитывали,
Yes, we have not yet
но для
calculated this
300
task,
киловатт будет
but for
достаточно
300
текущего
kilowatts,
катода.
it will be the current cathode will be sufficient. Thank you.
Ну, тогда еще раз поблагодарим.
Okay, let's once again thank you, Mr. Maxim. Let's thank Mr. Maxim for the report. And now we have
Небольшой 20 минут,
coffee
и
breaks
после
of
этого
20
возобновим
minutes.
работу
And
сессии.
after this, we
Всем
will
спасибо.
continue. Thank you.
Кстати, видел еще один доклад отменился. Еще два.
Вот еще я как раз хотела сказать. Там, значит, смотри.
Вычеркнул 20.
Вот, это значит, сейчас пошел у нас этот. Да, сейчас пойдет Стальков. Потом, значит, потом Елисеева и этот самый Меркин отпадает. Да, Терентьева, нет, у Рожкова, потом идет Терентьев, потом у Рожкова с Ворошкиным один доклад. Вот. Вот, ну как, я заберу, господи, как. Потом ты читай Семенова первого, потом я заберу Семенова второго и Козырева. Потому что потом идет Осипов и кто-то там, и Дураков, а Паршуков и Ластовире их не будет.
Пашкова не будет?
Паршукова не будет.
Да, это вот сказал.
Вот. И Ластовире тоже не будет. Поэтому, соответственно, у тебя Кожиченко не Хорошев, и я Чулкова зачитываю. Вот. Окей? Поел? Я тебе блинчик принесла, ешь.
Я один съел.
Так я тоже съела. Что это тебе?
Люди исчезают.
Ага.
С утра так было, сейчас уже по-другому.
Ну да.
Это может как раз по поводу которого сомнений ты высказывал, что он что-то хрипел, что-то еще что-то.
Да, бог его знает, что там. Так, ну 20 минут, можно это. Это фигня, тут меня все раскидало. Так, ну что, что-нибудь подумал насчет моих переводов-то?
Ну ты еще какие письменные люди?
Ну, я так понимаю, и письменные, и устные. Устные, я так думаю, что...
Письменные они у тебя уже есть, да?
Да, полно. Полно.
ты скажи по объемам, по срокам.
Вот, в том-то и
по
дело,
оплате.
что там, да,
Если что, бери бананы, я притащу.
хорошо, спасибо большое.
Они, правда, так темнеют быстро начинают.
Ну, это нормально. Это,
Я
да
тебе
сюда
мусор-
кидай,
мусор
кидай,
думаю?
кидай, кидай. Так, давай я посмотрю, там просто видишь, зависит от того, как сказать, что тебе удобнее будет взять. То есть, допустим, те же вот визуальный контроль, они все одинаковые, но там много башкотни.
Мне видишь, если ты мне дашь шаблон какой-нибудь, то тогда...
Шаблон там все равно надо проверять.
Нет,
эту
нет,
самую.
это понятно, я имею в виду,
Вот.
что, по крайней мере, мне не набирать заново сидеть.
Нет,
эту
нет,
таблицу
конечно,
там
рехнешься. Нет, это шаблон я могу дать. Это да. И это без всяких, но там, я говорю, просто там вот муторно, там сидишь и проверяешь вот эти вот все средства измерения. Есть такое.
Это я не очень люблю, честно говоря.
Вот, я про
просто
это и
так.
спрашиваю. Я тоже это не очень люблю. Поэтому я очень люблю, когда они присылают их в редактируемом формате, их просто в радость загоняю. Вот. И, соответственно, это. А если, допустим, паспорта-то тоже
Да
ты
нет,
можешь
пофиг, если
делать.
надо, так надо, что ничего.
Надо посмотреть
ничего
просто,
страшного.
надо посмотреть.
Мало ли,
тогда.
что я люблю. Какая разница?
Дело в том, это вопрос скорости и усталости.
Ну,
Вот.
согласен.
Ладно, окей. Давай тогда, короче, я посмотрю.
Давай.
И скину тебе, посмотришь, что там как у тебя время, то все, тра-та-та. Вот. А так, в принципе, тебе руководство-то позволит уезжать на это, ну, на устный перевод?
Да, я думаю, сюда, но видишь, я сейчас все равно только паузу взять.
Ну, конечно, естественно.
Такой херак и уехать.
Ну, да-да-да. Ну, то есть, естественно, руководство надо предупредить. Вот. Потому что это... Но...
Ну, там все-таки по продолжительности это лучше, удобнее-то как это, чтобы было неделя прям, или как вообще? Вот я...
Зависит от того, насколько ты сможешь. Видишь, в чем дело? Допустим, если ты сможешь приехать на 3-4 дня, потом, допустим, я подхвачу. Это нормально.
Вот. Они приезжают, ты говоришь, хрен знает, насколько они.
Они хрен знает, насколько их вытащат, настолько они приезжают. Потому что никто не знает. Ну, то есть все уже поняли, как они работают, поэтому там чуть ли их не на месяц сюда засылают. Потом вот должна, да, то есть вот вчера должно было что-то начаться, ну, в другой компании. Они не приехали, они еще из Каиры там не выехали из своего. Вот, и поэтому, соответственно, тут как бы вот так. Но они приезжают надолго. То есть...
Тем более там ситуация еще такая непростая.
Ну, это, знаешь, никого тут сильно не волнует.
Нет,
главное оборудование обгрузить. Поэтому,
вот,
соответственно, вот, ну, просто я к тому говорю, что вот по поводу проживания, как у тебя там? То есть это все-таки другой город?
Нет.
Нет, ну где-то же надо спать, я не знаю, там помыться,
нет,
то
как
все.
бы, что там, у меня и мама там, и сестра.
А ты у мамы и сестры сможешь нормально неделю жить? Они не скажут, что, господи, боже мой.
У сестры нормально вообще.
Нормально?
У мамы вряд ли.
Ну вот я про это и говорю, то есть есть
Это
спать?
потому что правнук еще живет. Нет, спать-то где, это вообще не вопрос. Это такая нормальная.
Ну просто я к тому спрашиваю, деньги на это надо будет тратить компании или нет? Вот о чем речь.
Нет.
Вот. Хорошо, то есть насчет дороги?
Попросить.
Надо спросить.
Да нет, ты что?
Надо. Ну нет, насчет дороги-то я думаю, что это, они там это все дело как-нибудь организуют.
Я никогда был в гостинице, мне же даже не представляю. Я не представляю, как это выглядит.
Ладно, хорошо. В общем, короче, сейчас эту бодягу мы закончим. В смысле, это мероприятие. Потом я со своими бодягами разберусь. Что там, как, куда посмотрю. Спрошу у них вообще, какие
да,
там
вот тоже
планы.
по срокам, чтобы я примерно
Да,
прикинул для
конечно.
себя, по крайней мере.
Конечно.
То
Сначала
есть
я тебе отправлю что-нибудь
на работу
срочное.
выйду. Нет, я имею в виду не по письменному,
Ну,
даже вот по устному. То есть
да,
я посмотрю,
да,
когда есть какие-то
да,
вот
да,
такие
да.
варианты более-менее такого затишья, что как бы нахер ты никому не нужен уже, то уже там, чтобы запланировать. Ну, я имею в виду, что...
Просто вопрос-то в том, что я говорю, что вот желательно это все-таки, чтобы человек-то в доступе был, ну, таком относительном хотя бы. Вот понимаешь, в чем проблема. Вот. То есть, если, допустим, у тебя на работе сейчас под конец года завал.
Да нет, там вряд ли какой-то завал. Тут просто видишь, что даже больше не с точки зрения загруженности, а с точки зрения наглости. Ну, что типа там такое, чтобы там уж не наглеть, так тебе не сказали, а может ты нахер тогда уже вообще туда переедешь? Например, я имею в виду.
Нет, а подожди, ты же не на госслужбе, ты же имеешь право другой оплачиваемой деятельностью заниматься, что такого?
Нет, это не в этом плане, что как бы, чтобы там это не было там, как бы не вошло в привычку, что там раз в неделю ты уезжаешь на неделю.
Нет, может быть и такое, но я говорю, этот проект не будет длиться вечно.
Я просто, нет, я к тому, нет, это я все понимаю. Я к тому, что тут как бы тоже надо так, знаешь, с точки зрения
баланс
психологии,
искать,
подходить,
конечно,
какой-то
да,
баланс, чтобы так не то, что
Ну,
чтобы потому
все
что
понятно,
ты
я
не
понимаю,
наглеешь,
да.
совсем,
Хорошо. Ладно.
Поэтому надо тоже это все будет посмотреть. Сейчас-то, конечно, до конца года вряд ли что-то будет такое запарное, потому что уже, в общем-то, уже
То есть у вас под конец года не цейтнот?
Ну,
у
нас,
меня у
нет,
всех
у нас,
сумасшествие
честно,
начинается.
бывает иногда, у нас потому что министерство наше долбанное образование московское, оно любит всякие отчеты, чтобы готовили. Причем это какая-то такая хрень, которая, блин, делится на несколько человек, то есть у каждого там свой набор таблиц, которые ему нужно заполнять, всякая статистика. Хера они это делают, я не знаю, куда они это все. Это, как правило, знаешь, перед Новым годом, там чуть ли не там. Ну,
то есть
31
кто-то проснулся
числа,
и вспомнил.
конечно,
31 выходной день, кстати.
Я просто говорю,
я поняла.
Ну что, как-то там они вообще это почему-то именно вот.
Так, пойду я. Тут пузель, значит, работает, да?
Да, там два, но я
А
всегда
там,
в первых хожу.
прошу прощения, бумага есть?
Бумага вроде есть. Термос какой? Вот этот?
Вот этот термос, да, вот это вот мои RD-шки большие. Так, стой.
И затычки.
Да, и затычки. Перекидос это у Худи, да. У меня свой перекидос лежит. О, как ручки красивые.
Подрежем.
Вот, ну,
Ух ты, да, сюда хорошо.
можно будет бананчик. Нет, я тут отправляю ссылки.
Что-то, кстати, на самом деле ощущается, что это прохладнее.
Ну,
По сравнению
видимо,
с
там как бы
там.
все ходят это.
Там еще
пока-
окон, потому что нет.
Да.
Около окна идет.
Нет, там в фойе же есть окна. Нет, просто это. Ну, короче, тут, мне кажется, нет же одной фрамуги, вон тут вон. И чё?
Good day, dear participants of the conference. So my report is dealing with the electron beam modification of polymer matrix composite material. So modification of the surface is the change of the surface structure and properties when affected by the power source. So the modification allows today increase in the hardness of the surface, wear resistance, and decrease friction coefficients. So the surface modification was made on electron beam plant ILTEC 34412 by NT Progress, and the composite material was produced by Bauman Moscow State Technical University, and it was the base of aluminum material MG3 plus silicon carbide as an additive. During treatment, we used two types of rimmings. So it was one is straight, and one goes 2 and 4. So the second one was a pulse one. So the points were put on the targeted setup distance from from another in such a way as to minimize the heat treatment of adjoining points upon each other. So there were gaps with further returning to the neighboring point. So to select the modification mode, first we process the samples from aluminum alloy MG3, and on all samples we got the satisfactory formation of surface. However, in mode 2, so it was a failure. So there was a smaller roller overlapping, so therefore the fusion depth was smaller. So the first two samples, so the rimming type was direct straight one, and in the second type and fourth type, so they were pulse ones. So and here you can see the results. They are demonstrated in the table, and so there were also some defects like cracks, cuttings, and we also use matrix composite materials, and now we are going to discuss the materials. So when processing the composite materials, and so the straight rimming, so we got the stable surface relief, and we measured the fused a layer of both samples, so it increases due to high heat conductivity of aluminum. So when we use the pulse mode, so we got smoother surface. Also the fusion depth increased, and so there are also defects, unfortunately, connected with the method of producing the composite materials. So it was produced by casting, and we only process it. And after the treatment, we investigated the microstructure of the samples. The base metal, it was solid solution of aluminum with secondary phases on the phases, and also in the metal there were eutectic. The presence of intermittent strips of aluminum and chromium phases, and after treatment, the structure was separated into three types. So the first type of microstructure is characteristic for the majority of samples: solid aluminum, solid solution of aluminum, so with the dispersed inclusions in all grain sizes. And the second type of the structure, it's only for mode 5. And these are small grains of solid solution with secondary evolved phase. And the third type, so the size of the grains was 10 micrometers. In the second, 50 micrometers. Now this structure is close to the base metal. To find the mechanical properties of the samples, we measured the micro hardness of the samples, and the highest value was at mode 2.6. So the micro hardness of the base material was 42, and so the final product 57.7 HB, and mode 6. So initial and final types, so they are the same, and so the mode. It was pulse rimming used with high speed, 1200 millimeters per minute, and also with a reading of 24 hertz. So the decreased hardness is observed on some samples due to the evaporation of magnesium from the surface layers, because magnesium has a high vaporosity degree, so therefore using using this reaming, so it was possible just to decrease the evaporation of magnesium, and also due to the grain size, we managed to decrease the cooling rate of the surface, therefore increasing the hardness, improving the hardness. So we can make such a conclusion that electron beam modification of composite materials allows increasing the surface hardness, but it's necessary just to choose the heat cycle of the obtained layer. So, and with the help of pulse reaming, we managed to do this, and the best results were actually received with this type of reaming. Thank you very much, Elizaveta. Questions, colleagues, dear colleagues? In the picture with the structures, the best variant which you said it was the most defective, or maybe it's not a good picture, not a good image. So it's a composite material, and it was obtained in such a way that the chromium carbide, silicon carbide powder is placed inside, and maybe the method of producing it is not actually a perfect one, and so therefore the inclusions of the carbides are present, so therefore the structure is not that uniform. So sometimes we have more reasons, sometimes less, but if you're talking about the cracks on the surface, so these are caused when preparing these surfaces during grinding, and there were some scratches on them. We're talking about silicon particles which are not present in this mode, but in other modes the heat input was higher, so the sample was heated up to a high temperature, so therefore silicon was only on the boundaries of the grains. And the secondary phase of the boundaries of grains is also not good. In some modes, you managed to split up the agglomerates in some regions with the help of the beam. It was dispersive distribution alongside the whole volume, but you didn't get higher hardness. In mode 6 with higher processing speed, it was higher hardness. So this photo maybe is not a maybe doesn't from mode 6. Thank you. Other questions? Thank you for interesting report. As far as I know, so the processing of surface with electron beam. So usually in this, so the beams with big cross section are used, and the samples are usually heated up, and you didn't have, and so the gun which uses 6 kilowatts, so therefore we just demonstrated the results of using such a gun. So I also have just a brief question. So the electron beam technology by itself is quite expensive, and the equipment is expensive, and if we decide to use the results of your work in practice, so it means that we need the expensive equipment for that. And where can we use your methods in practice? For example, in producing the anti-friction alloys, unfortunately the colleague from Moscow Bauman State University didn't come, so they have studied after our so how the friction coefficient changes after the treatment. Also the wear resistance improves, and they got the results that the wear resistance increased in 1.5 times. And the friction coefficient decreased. And we all know that bebite materials are quite expensive, and possibly it's possible to decrease the production cost when we introduce new composite materials. Thank you, Elizaveta Pavlovna.
Okay, our next speaker is Igor Terentiev, Moscow Power Engineering Institute. I'm once again greeting you here at the conference. Today I would like to dedicate my report to the problem of receiving the combined titanium steel structures. In other words, these are the bimetallic structures. It is known that generally, if we talk about the relevance, we don't have any questions because producing the combined structures of steel to titanium is very relevant in many industries. So the wish to combine these materials is a very long one. But the problem is metallurgical incompatibility, and everybody knows this. So the attempts to combine these materials, to connect these materials, was started last century. And it became apparent that melting did not give any positive results for the apparent reasons because of brittle intermetallites, and it was decided to use welding in solid phase. The most widespread method is explosion welding, when steel and titanium plates are connected with a high speed of interaction, and probably as of today, this is the most favorable method of combining. But also in this, there exist some problems because overheating occurs, and brittle intermetallites are formed, and also defects are formed, and etc., etc. And even in explosion welding, it's very often that intermediate layers are used from the because titanium is a refractory metal, and from the side of the steel, this is usually copper or aluminum foil. As the method of producing in solid phase, diffusion welding is used. Direct connection is inevitably, we will see the brittle intermetallites. Because of the soft thermal cycle, we can avoid cracking, but nevertheless the compounds remain brittle, and here we must again use the intermediate layers. Usually they are used in pairs. If we talk about the fusion welding, we already know the capabilities of use of vanadium as intermediate layer. When we make the vanadium insert and weld it by steps with titanium and with steel, there exist a lot of papers on this topic, and also the problems exist here as well. Interaction of steel with vanadium has a very unfavorable area where a brittle sigma phase can be formed, and large problems exist regarding insufficient ductility of the compound. If to combine all the welding methods, all of these are limited by the configuration of the junction of the joint bimetal structure. There exist certain restrictions. With explosion welding, we can obtain a flat or cylindrical, more complicated but possible. With diffusion welding, these are practical, just only flat joints. And if to consider the popular additive technologies, the limitation by configuration of the joint almost does not exist. Any cylindrical surface can be obtained from one side of which was steel, and on the other side is titanium, and with other welding we cannot produce it. So in our work we try to investigate the possibility to produce combined titanium to steel structures through intermediate layers. This work was done under the RF grant, and within this report I would like to show the results that we show the part of the results that we have obtained in the first year. The second part will be reported to you a little later. My report is dedicated to possibility to produce the structure of this type through vanadium and subsequent depositing either with low carbon steel, nickel, or iron nickel alloy. Why we choose such an approach? Well, copper can be, of course, deposited into a refractory metal, but the copper and bronzes have two disadvantages: low strength of copper and strong difference in linear expansion coefficients, which also results in internal stresses and which will adversely affect the performance. Well, let's start step by step. So we started. We have taken a BT4 plate, and onto it we deposited some vanadium layers. So from the process part, we met some difficulties due to that vanadium has a higher melting point, and inevitably the titanium substrate melts significantly. So titanium content in the vanadium layer we could not reduce below 30% just because of the melting point. So if we reduce the temperature of welding, the surface melting was insufficient. You see the macro section of 3 layers of vanadium deposited into titanium and the plots of dense distribution by the section. We should pay attention that there are no bursts. We thought it would be possible, but in the transition zone, if we look at the diagram of steel to vanadium, there exists the area, first of all, where stainless phases can be formed, Martensite, and the most unfavorable is omega phase. But judging by the microstructure that we have checked by electronic microscopy, and also micro hardness we measured with a pitch of about 0.7 of micrometers. There were not found any hard interlayers. Even Martensite zone were about 30 micrometers wide. So the HV was 200 to 250 units. So I would like to pay attention that chemistry changes in bursts like there is a transition zone where the chemistry changes abruptly is about 30 micrometers wide. So you can see here. One moment. Need some exercise. Well, okay. Well, to the left lower angle, we will see the Martensite structure in the transition zone. Generally, if we speak about depositing of vanadium into titanium, we think that depositing of this type is quite operable. And in no specimens we found any cracking or fracturing or some other defects. So we don't expect many problems here. Here we should pay attention at the fact that since the substrate is surface melted significantly, we need to somehow remove titanium from the vanadium layer. But because the modeling results show that even the small content of titanium in vanadium layer shifts the sigma phase area to the left, means the higher the titanium content is, we can see to the right, the higher is the possibility of forming a brittle phase. So the graphic of dependence of probability of sigma phase formation on titanium content is given at the lower part. If the titanium is 30%, the sigma phase will form at any content of vanadium, and even in the steel. In order to avoid high content of titanium, we have to deposit a lot of vanadium layers. And in practice, in principle, we have seen this. For example, when we deposited a low carbon steel onto the vanadium layer with titanium content of about 67%. In the process of cutting out the specimens, there was fracture along the joint. Micro hardness measurements showed that the hardness was HV was 0.01 or more than 1,300. It can see in the picture. But on macro hardness, it can be skipped because the zone is quite narrow, but hazardous. Here, they're shown the results of examination of microstructure. We can see the area of brittle interlayer. To the left, it is about 30 to 40 micrometers wide, and we can see that the cracks most apparently existed there before the fracture, before we cut it out. Chemical analysis showed that in this interlayer, the vanadium content was about 26 to 27%, and titanium about 3%, and iron about 70%. If to judge by the diagram that we received on the previous slide, this falls into the area of existing sigma plus alpha phases. That's why we think that the brittle interlayer has the structure, maybe not of pure sigma phase, but the mixture of sigma plus martensite phases. And of course, the next step was to increase number of vanadium layers in order to remove titanium content to the minimum. Here we can see that this is 0.01%, but this is a kind of error of our spectrometer. And here I should remark that we managed to avoid at least the cracking and fracturing of the specimen. And what the most interesting is that despite the occurrence of interlayer, the hardness even it was maximum 380 units. The titanium in this case is quite well, it acts negatively onto the joint of vanadium to iron. And if we talk about the additive manufacturing, this should be kept in mind and controlled. At the moment, we have made the specimens and for tension test, but never didn't have time to make it. But I hope in future we will make a report and publication on this topic. Next. Apart from depositing directly, still directly onto vanadium, we decided to try nickel into vanadium depositing because nickel has a lower melting point, and we expected that it could be possible to deposit nickel with the minimum surface melting of vanadium. And the second is for the nickel, the sigma phase existence area is much lower and is formed with higher contents of vanadium. Here we met the same difficulty when in vanadium there was a lot of titanium. And again, a brittle interlayer was formed with a quite complicated structure. And some specimens, for tensile testing we did, they also fractured in the course of making. Here there are shown the results of microstructure examination. Okay, one nickel into vanadium depositing with high titanium content is shown. I will not tell in detail because, strictly speaking, we did not make examination for vanadium, but we can suppose that we're talking about the structures like intermetallites, like nickel to vanadium, and eutectics mixtures. This is regarding the structure, and this can be seen in the transition area. Okay, the next step was depositing nickel onto vanadium with low titanium content, and here we obtained positive results. Immediately after the titanium content was lowered down to minimum, we managed to obtain the structure without cracking, which at least stood cutting out, mechanical treatment machining, but still we didn't have time to make tension tests. But the positive influence we can see already. The next was that we decided to try to deposit the alloy of welding wire SV130, 50% ferrum, 50% nickel, and we tried to deposit this one. The results were a little worse, despite that the specimens were also stood all the process operations of cutting. And on the sections, somewhere we found micro cracks located perpendicular to the fusion line. They are not wide, you can see in the bottom picture, but unfortunately, this version we will not use in future. And of course, as the experiment, we tried to deposit austenitic steel 316L onto vanadium. We didn't have much hope because the chromium also deflects to the area of existence of sigma phase. So the first bit was deposited okay, but when we deposited the fifth bit, the structure was destructed in the course of depositing. It's clear that sigma phases in unstable conditions it doesn't have the time to form. So yet at preheating, or in repeated heating, when we make a next bit, preheating occurs, and that because of this, the fusion line is an unstable. In the fusion line, unstable fracture are destructed and they decompose. The more layers we deposited, the higher stress arises, the more sigma phase is formed. So, and this happened on the fifth bit. And the microstructure is shown on the lower pictures. You can see by yourself. Well, generally, this is all I wanted to tell you. These are the main conclusions. This, as you can understand, is the preliminary work. This is a kind of research work. And the results, and with the results, we're planning to proceed our work. Thank you. Do you have any questions? Thank you very much. Dear Mr. Igor, any questions? Could you please tell us what was the task you resolved? What was the task of your when you told that this could be made with explosion welding? So, probably your aim was some narrow task. So what was the point? Well, okay, you see, for example, one of the tasks which can be resolved using additive manufacturing is obtaining the cylindrical surfaces on internal side of which there will be titanium, and on outer side it will be steel. Explosion welding in producing such structure was due to several factors. First of all, if this is a cylinder, kind of circumferential cylinder, you can produce more or less significant. But with the explosion of two concentric cylinders, overheating of the gas occurs, and there are a lot of defects. And here we talk about obtaining the structure capable of repairable one if needed, and resistant to overheating. Any bimetals produced by explosion welding, they do not stand overheating. So at certain temperature, a crack or fracture will happen, and this structure will be able to operate at elevated temperatures also, and this is relevant, for example, for nuclear power engineering, where the structures are used, or steel to titanium structures are used, and this is also relevant because the operating temperatures are below 600 degrees, but if we talk about the long-term operation, it might be relevant. And owing to quite long transition zone, we can avoid here the unwanted diffusion processes. We consider the structures of this type as stable ones, stable structures capable of operating at elevated temperatures and be repairable. This could be able to weld titanium to titanium, steel to steel in these structures. And one small question about the structures that you received in titanium to vanadium welding. Where is the sigma phase? Did you do mechanical testing of these? Because it doesn't have a hardness burst, but the martensite ductility is different. You know, the question is, yes, a very good question, but well, if we talk about alpha martensite for steel, we cannot tell that it's very brittle. We didn't have time to measure it because at this step, we think that the more relevant is to resolve the problem of connecting the vanadium further with steel. But preliminary testing are planned by us to the nearest future, maybe a month, and it will be clear. Well, of course, we expect the problem area from some other point of view. Thank you. Another question, please. Proposal. What if to deposit not vanadium onto titanium and vice versa, titanium onto vanadium, because of melting points are different? Well, that's just perfect, but the limitation here is usually most of configurations of the products will require from us to start with the titanium or with the steel. If we start with steel, for example, to deposit vanadium onto steel, there will be much more problems because the vanadium has a different temperature from melting point from steel, and there will be a lot of admixture of steel into vanadium, and there will be more problems. And if to deposit it vanadium into titanium, we can skip these problems. If we do this structure vice versa, I think that there will be more problems in this case. Well, on one side, on structures of certain kind, it's possible. Say we can take vanadium workpiece and from it to grow the to different side. Yes, I think it's possible. In some situations, it will be very interesting and relevant and much simpler. Well, frankly speaking, to deposit vanadium into titanium is not our biggest problem within our work. But in this case, there will be less titanium in vanadium. Yes, I can see, but if I want to deposit titanium onto vanadium, the vanadium insert shall be made quite thick, because because onto any vanadium surface, we need at least 3 millimeters thick. And so, what's the point? We can make these 3 millimeters of several layers of vanadium onto titanium. In this case, there will be a lot of titanium in vanadium, but yes, look, it can be resolved. We depositing, say, 4 or 5 layers, the titanium content goes below 1%. Dear colleagues, I'm terribly sorry. I think that such kind of discussions can be skipped, and you can do it a little later during coffee break. We should have short questions and short answers here. Thank you. Yes, another question, please, Mr. Alexander. Thank you very much for your report. It's very interesting. In the summary of the methods, there is another method for heterogeneous metal welding. There is another method for stick-3 plants. They allow to make this kind of welds, and these plants were developed by Moscow Power Engineering Institute. So without any depositing, I will tell you the method if you need. We are welding now the rod type structures, and thickness up to 100 millimeters, and the strength of the compound is no less than the strength of the base material. This is another very interesting method. Yes, would be interesting. Let's discuss it. Thank you. Thank you very much. Thank you, Mr. Igor. So I'm sorry, no more questions. Thank you so much. According to our program, the next we shall have two speakers. They are slightly different because these are different companies, Perm Plant of Машиностроитель and Perm Polytechnic University. But as far as I understand, the authors decided to combine two reports, and we will have as a speaker Stepan Varushkin.
Good day. We discussed with Konstantin and we walked with him together. And I think it's very difficult to present our two topics separately, so therefore I'll make my report based on two topics. So my topic is dedicated to electron beam additive welding with vertical feeding of wire and heat input distribution on the surface. If we consider the traditional scheme of electron beam surfacing with side feeding of wire, as what I said already, there are a couple of peculiarities when the wire just shadows small area from the direct impact of the electron beam, and in this case we have the non-uniform distribution and a uniform picture on the direction of welding from the side where the wire is fed, and this results usually in the need to increase the total power just to guarantee defectless welding. And here on the slide you see if we need to melt the wire and then to deposit the layer, let's say 1.5 millimeters in this case, the fusion can be, penetration can be a few layers, and this also influences the deformation and mechanical properties. One of the ways to deposit the vertical wire with uniform action from all sides by the beam and the deposited area, the so-said X-beam technology, when we get the hollow electron beam and the wire is fed axially together with this beam. But in this case the technology is quite simple from the technological side, but from the point of scientific point and further progress, it significantly impedes the influence of electron beam on the area to be deposited, and therefore it's difficult to vary the area, the deposited area, and also the distribution between the wire and the product itself. And also it eliminates the deteriorated quality, but anyway, so we face some complications. The next technology is, from the physical points, is a simple one, but the realization, it's multi-beam influence or effect to the axial effect wire. Here we use 2 electron beams, and the plant produced by NT Progress. It's in Perm Polytechnical University, and the experiments were carried out on it. So the wire is fed from the outside through the ceiling, through these points, through the straightening mechanism, and vertically into the chamber. So the technology is also quite productive, let's say good one, and some initial experiments have been already carried out, but we don't stop on it, and we just move on to the topic of our report. So to to spread the range of the used input energies without deteriorating the quality of the deposition. And so actually we made the preliminary investigation, so we checked different reamings for this and also the distribution of the heat in the substrate and in the wire, and also we used on-site experiments and investigated the obtained results afterwards. Let me repeat, so just the wire is fed vertically, electron beams acts upon it from two sides, and so we also used the 8-digit type of reaming, so with the frequency 200 Hertz, and the action and the influence area is 4.5 millimeters, and so the speed is 0.3, and the feeding of the wire rate is 1.5 meters per minute. So what should we point out? So first of all, we prove the independence of the quality of deposition against the direction of the movement. So here you see the photograph of our sample with two directions in axis X and Y. So using the ruler, so we can check the dimension, the geometrical dimensions, and we can compare the independence of the quality, let's say geometrical quality, upon the direction of deposition. However, when we use the high walls filled in several strokes in chess-like order and wear in the directions of deposition, demonstrated that there is insufficient heat input, so the availability of defects, though the reflected electrodes it was not seen that well. So also we checked huge defect afterwards. So as we said, it was kind of a raw melting inside, and it should point it out that the directed growth of grains is observed from the first layer. So the modification of the reaming of electron beams, here we actually considered three main factors. So first, just to provide the symmetric uniform distribution of energy on the deposited surface, and it was actually done not to depend on the direction, the deposition direction. Next, it was to provide the action by electron beams upon the wire with the minimum density of power in the zone into which the wire is fed. So Dmitry Trushnikov actually touched upon this issue, and when in the center we have the local maximum in the center where we fed the wire, so it carries away the melt to the periphery. And the third principle, to provide the possibility to adjust the proportion of direct action by electron beam upon the wire and the surface of the deposited region. And analytically, we also move to another type of reaming. If we look from the electron beam gun, so we see it in such a way. It looks like a smiling face, but only from the number of dots. So it can be just separated into two parts. So the first part influences the surface to be deposited, and two lines are formed from this sets of points. And also the heat input, the direct heat input, is adjusted with the help of adjusting the relative action time between these two parts. In 3D picture, it looks like this. Two beams, symmetrical action upon the substrate and upon the wire. It looks like in the reflected electrons. So the print from one gun, from another gun with the wire. You can see the wire contour. And so the reaming is significantly bigger. So the prints from both guns at once, and you can see the symmetrical action in the deposited area. So the adjustment of the deposition mode, so it resulted in the increased productivity in 1.5 times. So we managed to speed up the feed rate of the wire, and also the other parameters, the deposition parameters and the distribution of input heat, 60% into the wire and 40% into the deposited region. And so the cut showed us so we saw one defect, and then the previous table was took into consideration such mechanical defects. I'm talking about the microstructure, so the directed grain growth, and we see the activity only from the third layer, or maybe from the middle of the third layer. Mechanical properties were investigated on the samples obtained with different filling types. So these are 100 millimeters with the height 100 millimeters and 80 millimeters width, and the thickness about 15 millimeters, and also the longitudinal filling, like a chest-like mode, and with cross one, transverse one, with transverse oscillations, and with the oscillations at 45 degrees, and the results are demonstrated with the oscillations slightly below ghost figures for the rolled materials, filling with longitudinal tracks, and this was in compliance with the ghost state standard. So both in hardness, plasticity, in the form of relative elongation. So the material macrostructure, if in the bottom part we hold the water cooling substrate, everything is clear in this case. We also investigated the top part, and it should be pointed out that the deposition was a continuous type without any cooling pauses for cooling, and we can see that the deposition with the oscillations at 45 degrees contains very wide initial grains. Deposition with cross transverse oscillations, so they are narrower, and with filling with straight rollers, we see some waves of the wavy structure of initial grains. And as conclusions, I would like to tell you that the modified technology we managed to get to the production of 0.45 kilograms per hour, but unfortunately this doesn't allow us to deposit in this mode, to deposit the walls with multi-pass filling in width. The use of distribution of heat input helped us to increase the productivity in 1.5 times, up to 0.66 kilograms per hour. And so the mechanical process of the material, as it was demonstrated before, it's in compliance with the level of for rolled products. And in our plants, it's necessary just to have smoother structure because we had a rough one. And so this is the task for us, just to fill the gaps, the pauses between the weldings. So this is it. And also, as a conclusion, I would like to say thank you to NT Progress for their support, and also just to give them a present of this modified wall made on our plant. Dear colleagues, I have it's like a semi-question, let's say. So vertical growth of grains. At the last conference we talked about this, and now we're also talking about this. Those who are dealing with additive technologies from wire, let's take such an obligation on ourselves that we manage, that we won. we'll declare it on the next conference, and actually without rolling, without heat cycling, just we managed everything. We managed it. And also we have the proposal to the universities, so the units that can be used for additive technologies and experimental works. So we have them in sufficient quantities. Of course, we yesterday we showed you, demonstrated you the plans that we have, but we cannot give it to everyone. And so we'll send this informational bulletin to all the participants of the conference that we are modifying our plans for a long period of time. So you can come to us with your wire and just test it. And you will have our plant and also our metal graphic laboratory. So this is my proposal, my suggestion for the next conference, that we will declare at the next conference that we managed, that we won this problem. Thank you very much. Thank you for your report. Questions? Thank you. So next is the organizational issue. So Mr. Pavel Stalkov was supposed to arrive, but he actually hasn't. Is Yuri Semyonov here? Then we should make the decision, because Semyonov has two reports in a row. So we have 30 minutes before the lunch break. Either we go to the lunch now and return earlier. So we don't have the next speaker at the moment. And after Semyonov, we have Parshukov. Durakov is going to make the online report. Vasily. Dear colleagues, also another organizational issue, the lunch. It's 50 minutes, it's planned for 50 minutes. Probably we'll ask organizers to make it 1 hour. And as we are locals here, so we recommend two options. So we have two cafes. So it's possible to go to these cafes, and it will take not more than 1 hour. One cafe is Kino. There are two persons here, Petrovsky and Davlechin. So they have lunch there, so they can just accompany you. Just please raise your hands so they can take you to Kino. And another one is Еда навсегда, Food Forever. So it's a little bit further, but just like 230 meters from here. So I usually have lunch, yeah. So therefore I can go with you. You can accompany me to Еда навсегда, yeah. So there are two options. Okay, so we'll give Mr. Durakov the chance to make his presentation. Yeah, of course. If you have questions, then you should use the mics, because otherwise the speaker won't hear you. So then, if Mr. Durakov is ready, so we can start with his presentation right now from the next session after lunch break. But if he's ready, we can start now. The application of electron beam welding in the production of vacuum heat insulated pipes. Vasily, please go ahead. Do you hear me? Yes, we hear you. We are listening to you very attentively. Good day, dear colleagues. I'm happy to present my report. about electron beam welding in the production of heat-insulated pipes. I am the representative of a scientific productional company Kuybay Neftimash dealing with the production of equipment for oil extraction, including heat-resistant ones, such as slides, valves, thermocouples, and so on. But relatively new products for us is the production of the heat-insulated pipes. And so we have not been quite long present at this market of heat-insulated pipes for a couple of years only. There are other manufacturers with longer history, but we had such a complicated task. It was necessary for us to demonstrate that our pipes are at least on the same level from the quality point against versus other manufacturers, and I would like to tell you how we succeeded in it. So next slide, please. So it's my report. So the characteristic features of wall. Yeah. So first of all, we are talking about increasing the world structure, the world share in the oil deposits. So first of all, we are talking about heavy oils, high viscous heavy oils, traditional oils, and oil sands and bitumens. So actually, we have been talking about this for years, and but the situation is still the same. In Russia, the situation is similar. According to different sources, the share of difficult to extract stocks of oil, it's practically the same, and it increases all the time. It's anyway, so we have to deposit it. Talking about high viscous oils, and they have one peculiarity. They have a sufficient number of microelements, vanadium, nickel, chromium, molybdenum, and from this point they are also very interesting. To extract heavy, high viscous oils, it's necessary to use heat technologies, and they are quite developed in Russia. And what is the sense in these technologies? We pump steam, overheated steam, up to 150 degrees into the well. So and after that we extract this stirred material, and so it's basically pumped from the pipe. And usually to do this we need the heat insulated pipes. So what are the requirements for them? The most important is, as oil is extracted in the conditions of early frozen periods, so for heat conductivity of the insulated pipes, it's necessary just to preserve the energy. And we are talking about so the operation of heat-insulated pipes, it usually provides, first of all, the preservance of integrity of cement stone in the operational column and operational well, because if we pump the steam using the ordinary pipe, so usually it results in breaking the well, and actually it's very expensive equipment. So next is the prevention of hydrate formation. This mainly refers to extracting gas, because gas is usually extracted in the form of a liquid substance, not in gaseous state but in liquid state. And usually in deposits it's quite hot, up to 100 degrees. And if you extract it using ordinary pipes, it gets cooled, and the crystals form. Therefore, the diameter of the pipe is decreased, and therefore the well is narrowed as well. So heat insulated pipes, they just prevent this hydroformation. So next, to deposit oil, excluding the deposition of paraffins on the walls of lifting pipes, because sometimes there is paraffin in oil, and sometimes it can be deposited on the walls. And then heat insulated pipe allows to use it and to work in multiple heat loads. And it was checked on our pipes. When we use these heat insulated pipes, it allows increase the oil extraction from 6 up to 28%. It's according to the information of Usinskaya oil deposit. Here you can see the picture or the image of heat insulated pipe. So it's small one. I will explain. So how it looks like. So this is a pipe inside the pipe. So they are welded together, these two pipes. And the inner space between the pipes contains the screen vacuum insulation. I will give you more details about it later. On the internal pipe, we have centrators, which center the position of the internal pipe, and both pipes are connected with the help of ordinary sockets. And together, the sockets, and so there is no vacuum insulation in there. It's necessary just to use fluorine plastic socket, and it has some heat insulation, though not sufficient. Here you see the characteristics of heat insulated pipes. And I would like to draw your attention to the bottom line. So we try to get the heat conductivity coefficient not more than 100 W per micro. Yeah, so actually it's the requirement of Gazprom. And talking about the heat conductivity, so we have the results when the steam is pumped at temperature of 350 degrees, but Gazprom recommends to have the fluid temperature up to 100 degrees. So which means that the internal pipe temperature, when it's about 100 degrees, so this coefficient will be much smaller. I will just briefly show you the technology of pipe production. So it's 9 meters long, or 9 to 10 meters long. So it's preliminary processed by ball spurring. So we have the vacuum system, and vacuum needs the cleanness, and so we clean this. We polish it, both pipes from inside and from outside. Then we place the screen vacuum insulation. It looks like the repeated layers of aluminum foil, for example, glass grid. Foil, as a rule, is perforated for pumping later. And on the internal pipe, we put getter. So it's in the form of tablets produced by local manufacturer. So it's titanium, zirconium composition. It allows to maintain the vacuum inside the pipe during the whole service life. As actually the pipe is the soldered vacuum device. So the task is for the vacuum in the pipe to be preserved during the whole service life of this pipe. So so here you see welding. After the insulation is wound, so the internal pipe is inserted into the external one, and so there is welding on both ends. So it's a standard operation. And so welding by wear in the medium of protecting gases. So each pipe, welds of each pipe, so they are tested. and it very rarely shows the defect in welds, maybe 1 for 100 tests. And so basically we are not looking for the leakage, but for the welder to know that their work will be tested. For welders, to be careful that they are controlled. So pumping from the pipe, basically it's quite a complicated task, because when we had such task initially, so to pump everything from this pipe 9 meters long, and this inner space between the pipes is about 1 centimeter, depending on the type of the pipe, from 5 to 15 millimeters. So it's the thickness of the interlayer between the pipes. And so actually it's also filled by several layers of screen vacuum insulation, and all this to be pumped out and to get and therefore this pumping is carried out when heating the internal and external pipes up to the temperatures of 350, 400 degrees during about 30 hours. And we have diffusive pumps for pumping, and here you see the plant where we have the 500 pump, and 8 pipes are pumped at once. It's quite fast. Here you see the process of electron beam welding itself. Why is it applied? Why do we do it? So it's quite simple to pump, and it's standard technology. Everyone can do it. But a very delicate situation is the sealing of the hole. So sometimes we even use the cap, the screwed cap, just to close this hole. And so this unit cannot work for a long time. So we say that it's possible just to pump it again and just to generate vacuum. But unfortunately, if the vacuum was of not a good quality and it was heated up to 350 degrees, and with the bad vacuum, which means that it's already spoiled. And when we pump it again, so the situation will be only worse. It won't be improved. And so the vacuum inside the pump won't be preserved, because the electron beam was the tool which helped to solve this issue 100%, just to exclude the drawbacks completely, practically. And we have less than 1% of rejects. And sometimes it only depends on the operator, not on the technology. I can also add that we use gun for welding. And so the voltage is about 40 volts. It's not less than 100 megaamperes, just like in 2 strokes, 2 passes, and the second pass is for melting, just to make it looking beautiful from outside. And actually in this case the pipe is ready. Here you see the scheme, just explanatory scheme, just demonstrating the whole process. I would like just to show it again. So the electron beam gun, in this case you see that it's located on a special stand, and it moves on rails just along all the tubes to be pipes to be vacuumed. So it's installed, so it generates vacuum, and it takes about 5 minutes. And the installation time for the gun is not also more than 5 minutes. For other several minutes we weld the cap, so it's done manually. There is a special device And so this mushroom cap, as you can see it in the section, cross section on the top in the right. And with the help of a fork, this cork, this cap is inserted inside the hole, so it looks simple. Also on this picture you see on this scheme, so the tanks heating up the pipe from inside and outside. So the heating is not only for degassing and pumping, but also for activating the lateral. And so we need a temperature of about 400 degrees for the generation of it. On the right, in the bottom, you see the structure of the weld. And so the depth, it's about, welded depth is about 4 millimeters. And this is a controversial task to easily insert the cap. It's necessary to have certain gaps, and just to have it properly welded, so the gaps are supposed to be as less as possible. And so the gaps are about 0.1 millimeters, and it's possible to do it with the weld. So probably it can be a cone shape, but in this case it's necessary to choose to produce the cap with the proper height. If it has the cone shape. After that, after welding, it's standard machining. So you see just machining, threading, it's done on CNC machines. And here it's just ordinary lathe. So the quality criteria for the pipe is checking its heat and physical properties. How we do it? You see here on the picture, we have these endings. So these are the tanks inserted inside, heating elements inserted inside the pipe. So each pipe is heated up to 350 degrees. And from outside, and then the temperature is measured from outside. So there are about 15 meters at the ends of the pipes. We measure the temperature at the ends, also between the centrators, and finally we check the average temperature. Here you see the histogram of distribution of this difference in mean temperatures and room ambient temperatures. So usually the ambient temperature is about 20 degrees and the surface temperature of the pipe is about 20 degrees. And so this, about 40 degrees, and delta T is about 20 degrees. So 20 degrees of delta C agrees with the ratio of about 0.1. And here you see that up to 20 degrees, 22 degrees, so about 90% of our pipes agree or comply with this criteria. All these diagrams are made just at the beginning of the technology development, and now we have even better results. Next. So these are the results of heat physical tests. So how do we calculate it? We have the formula, standard formula, and this formula is used when calculating the heat conductivity coefficient and spaceships. So they use similar screen vacuum isolation. We inserted this formula in Excel document, and in the bottom you see the table into which we enter the temperature, 350 degrees of internal pipe. We measure the outside temperature, 45 degrees. Then we calculate delta T. And in the end, the computer calculates the coefficient of heat conductivity coefficient. And usually it's about 0.1, not more. Here you see the ready-made pipes, our shops, and the products stored outside and then shipped to customers. Thank you for your attention, and I am ready to answer your questions. Thank you very much, Vasily Grigorievich. Questions, please. So this is the question, yeah, from the end of the hall. So the work is quite peculiar, I should say, because it's quite urgent for oil and gas extraction in the eternally frozen areas. Because it's necessary first to warm up what is extracted, and the pipes are heated up from inside and outside. There is always frozen soil. So therefore, the technologies which we are discussing in this proposal, done in this work. So basically, this work is very complicated because they just pump this pipe first, and afterwards the welder inserted this cap into the pumped hole and just tried to use arc welding to weld it fast, and which means that by the end of the welding process no vacuum was actually remained, and Vasily suggested to use electron beam welding. Just be pumped and we inserted the cap and we used electron beam for welding, and maybe Vasily will tell us in the end of this discussion that it was actually a very positive and advantageous result for the company. I would like to clarify 2 points. So the internal diameter of the pipe and how the processing along such a pipe is carried out. Thank you for your question. So we use different pipes. So the information was on the table, but I didn't just maybe concentrate the attention on it. And so the thickness of the wall is about 5 millimeters. Internal pipe is 73 millimeters. The wall is 5 millimeters. But from outside, how to process it from outside is clear. But in order to make it from inside, so we use special device for this. It's like a hose, and so the balls are fed by the compressed air through the hose along the whole length, like 9 millimeters. Or the head moves inside the pipe along the whole length. Nothing complicated, just mechanical procedures. I would also like to add, first of all, thank you for such advertising. Actually, yes, so the use of electron beam allowed significantly decrease the amount of the rejects, because previously we had the rejects about 10%. And now, if for example, now they just complain if, for example, out of 100 pipes, only 1 is rejected. So you see how the quality got improved after the application of electron beam welding. Another question. Please tell us, so it's clear that vacuum is supposed to be inside, but why such a high degree of vacuum? Yeah, so the answer is simple. So because the free move length, it's a characteristic size, it's about 10 millimeters, or it can be like 1 millimeter in between foil layers, and -4 degree. So yeah, actually it's the criteria, we tested it. So for example, if it will be less, so the heat conductivity will sharply increase. Yeah, actually we tested it with -2 increment, and heat insulation actually deteriorates. So we also make it maybe a bit more. So actually we have -5 increment actually with the help of the pump, but it's just like to be on the safe side. And the pipe is supposed to be operated not 1 day, not even 1 year. And the best is the vacuum. Afterwards, it will serve for a longer period of time, because it's like a soldered device, vacuum device, and it's like the guarantee for all service life. So we have pipes which were stocked for about a year. So we tested them after 1 year, and so we tested them, and the vacuum was preserved because they successfully passed the heat physical testings. Another question, please tell us the control methods of welds. So how do you carry them out? So you're talking about the control method of electron beam welding? Yes. When we weld them, we use just visual inspection, no other methods. Another criterion is heat insulation testing. If it's not losing heat, so then everything is all right. If, for example, there will be some difficulties, yes, some deterioration in the quality of the welds, so there will be some defects. The following tests will demonstrate that the pipe won't pass this, won't achieve these parameters, and actually this could be revealed only afterwards during the operation. No, so therefore. About 10 days we check it, and afterwards, after about 10 days, we have final testing, and if it meets all the requirements, if there are some drawbacks, if it doesn't meet the requirements, if it has some drawbacks, so then they will be revealed immediately. So thank you, Vasily Grigorievich. Our distant participant, talking about our plan. Now we have the lunch break. And the lunch break till what time, please? At 2:20 p.m. we'll just continue our meeting. Неожиданно. Я просто нажал между собой. Ну что, выпускаем дураков. Так звучало очень прикольно. Пускаем дураков. Да, пускаем.
Смотри, у нас все остается. 2 Семеновых, Козырев, Осипов, Жуков уже все. Где-то там Стальков может быть появится, может быть, не факт. Ну, соответственно, Кожиченко и Нехорошев и Чулков. Я говорю, давай Семенова-то заберу, час болтал, как это.
Час там?
Ну, почти час. Не, ну сколько, вот 2 доклада у тебя прошло, потом этот на 20 минут опять выперся, даже не на 20 минут, а на полчаса.
Ну ладно, хорошо.
Соответственно.
Может, так неожиданно, что вы его...
Да.
Нет, хорошо, что чувак был в этом.
our work. The next speaker is Pavel Stalkov, Smart Equipment Factory. Dear participants, dear colleagues, the report is called the Plant of Electron Beam Welding, Soldering of Heat Exchangers. The plant is intended for the following. In domestic industry, mostly in aerospace industry, heat exchangers are used of very high pressures, and that's why they used the technology of soldering with high temperature solder. The technology is the tube. In a tube sheet, the tubes are very thin walled, and on the diameter of a product of suppose 60 millimeters, there might be several hundreds of these pipes. In order to solder all this with guarantee, the product is installed vertically, and onto a tube sheet there is placed a solder in the form of powder, a fine grain powder, or cut foil, or cut thin wire. Then from the top there is supplied electron beam, which is unfocused and makes some scanning of the surface. Heating takes place up to temperature of about 1050 degrees centigrade until the solder becomes liquid. Then, according to the superficial tension force, the connection is formed near each point and quite dense vacuum connection. As of today, we use the plants produced back in 1970s and 1980s, LT313, which are morally outdated and physically very worn. And to replace these ones, our company has developed this new kind of a plant. This is a render. This is how it looks actually. The picture was taken maybe a couple of days ago. It is almost finished. It is under adjustment step. The vacuum chamber is cylindrical with semi-elliptical heads, and the door is folded to the right. On the upper flange there is installed electron beam gun. A PA 120. This is the gun initially intended for metallurgical industry for melting refractory metals. Here it works not in its mode, but at less power. The gun is produced by LT Plus from the city of Zelenograd, our partner. This is the internal arrangement of the chamber. Inside the chamber there is installed the rotary table. The rotary table, according to the technical assignment, the biggest size of heat exchanger is height of 600, width of 200, and by 400. So we will have a quite large product. Either it's a charge of several small products can be done. So underneath the electron beam, only one product is placed. Afterwards, the rotary table rotates 120 degrees, and the melting of the next product is done. Peculiarity of the electron beam gun is that a very wide sweep angle, 45 degrees. That's why the size of the chamber is selected, and so that to cover the sweep to the maximum degree. The maximum circumference is the diameter of 600, and this corresponds to the customer requirement. Please pay attention how the fold door is done. Here is the boundary of detachment. And it turns out that with open door, about a third of the table is outside, and this is convenient for operation. For the operator, it's very easy to charge and discharge the the finished product. This is how it looks actually in real life. Here you can see that there is installed the gun. The gun is a diode type with a tungsten cathode. Cathode heating type is electronic, and cooling is with air. This jacket is very big. Inside it, the fan is installed. The characteristics of the gun: maximum current of 4 amperes, anode voltage up to 35 kilovolts, beam deflection angle of plus minus 45 degrees. There exists additional nozzle for pump, also the gate installed, and with the air cooling, as I already told you. The vacuum system is built on electric arc pump of homemade design. Why we use this pump is that the technology is different. The solder can be in the form of powder, but in some cases there is used solder with organic binder. You see, it's a kind of it's a kind of putty, and when it is heated, the organic binder decomposes. And initially we had the idea to put a cryogenic pump, but we understood that the product of organic binder decomposition will just kill this type of pump, and we will not reach the aim. And the arc pump is quite acceptable for it. We had to make it by ourselves. The pump is attached to the plumb to the maximum short with a maximum short pipeline. The diameter is 400 millimeters. There is a gate installed. Here we have the bracket for installing the CNC system monitor. Additionally, we mounted the turbomolecular pump with the capacity of 2,000 liters per second, produced in China. In the bottom part of the pumping station, there is a unit for vacuum pump and Rousseau pump, produced by Vacuumash from Kazan. The Rousseau pump will facilitate starting of the arc pump because the required pressure it will ensure. In the plants that are already used, there was no such a boosted pump, and that's why the operators had the complaints that the loss of capacity were because long reach of the vacuum. In this case, there are no such problems. Control system. All the plant is controlled using CNC system. The one we use is based upon Linux operating system computer and SCADA software system, OpenSCADA. And yes, you know, these systems are free and not proprietary, so we can use it in any way. Since he has the first function of control of pumping out and automation, here we see the example, just the example. This is another mnemonic. In mnemonic, we can set both program mode of obtaining and manual mode of controlling all gates and valves. The process itself is scanning of the surface to be heated with the focused electron beam. It's specially focused with the spot diameter of 15 to 20 millimeters, and selecting the current and frequency of scanning, we control the heating of the surface. There are two moments. If there is the unheating, there is no liquid phase is formed. And if there is overheating, the heat exchanger can be just killed. There's a very high chance. A heat exchanger is made of stainless steel, and we have to maintain temperature of 1050 plus minus some degrees. But if anything goes wrong, we will just burn a hole. This is very easy. Through selecting of the scanning frequency, we can clearly dose emission of heat and ensure the required mode. For monitoring, a Templar Vision module is used. These small spots are the pipes, and this rib is the stiffening rib which exists in this heat exchanger. It's installed vertically and just dissects this area into parts. This is just peculiarity of the design of the product. Also, they can be rendered both values of temperature received from the video image or reference thermocouples can be installed inside for calibration of the process. Still, the temperature is very high. With some skill level of the operator, he can just look into the window and by glowing understand everything. Well, of course, the instrument will be very useful in this case and also for the operator to calibrate it. In the conclusion, I can tell that the the plant that we have produced is the implementation of the existing technology, which is quite old, but it's unchanged and it was developed by the customer. They don't allow change of the technology, but implementation at the state-of-the-art level, our plant suits to the best. And once again, I would like to outline that why we used the melting gun, because it has initially a very wide sweeping. It's like a hammer, not like a gun. If we talk about the welding, it's an acutely focused beam, and we would like to receive thin weld. And in this case, we don't need this. We need just uniform heating of the wide area. That's why it's defocused and with a wide deflection angle and high power reserve. And it means that this gun will operate longer. It's like we won't load it to the full power. So 120 kilowatts here is just too much, I should say. In fact, the guns of this series, they are made starting from 60 to 400 kilowatts. The difference is the size of cathode. And the scheme they built at is very simple. The cathode is always in the gun in the mode of thermal restriction. The control is to the maximum degree simple. But for the set task, this is just perfect. The tungsten cathode, the cathode is tungsten tablet. It serves for a long time. The diameter, if I'm not mistaken, is 12 millimeter. And for more powerful guns, the diameter is 20 to 25 millimeters. It's fixed. It's mounted with quick release device with tungsten rods. In this way, we are solving the set task and promoting the domestic industry. Any questions, dear colleague? Yes, please, questions. If it's not a secret, who's the customer of this plant? The customer? Okay. There is the Teplak Enterprise. It's from Rosatom. No, it doesn't belong to Rosatom. It doesn't belong to anyone. Okay. Just a technical question. You said that you will check with the thermal visor. soldering is a kind of dirty process. So have you invented any measures that the thermal visor window is not polluted? The standard measures is a gate. The visor is outside the chamber. It's not inside. It's outside the chamber, and the we should introduce the correction about 2 to 3% for depending on the measurements taken in atmosphere and measurements on the glass. But this correction it's very easily to be introduced with a stroboscope. Okay, thank you. Any questions, please? I would like to apologize beforehand if you think it's a stupid question. You said that one of the technology options is that heat exchanger assembled onto it powder solder is put, and there is the system to rotating 120 degrees. What happens with the powder during rotation? How it's kept on the top? I understand how it can be put on the top, but how onto the other two sides of the triangle the powder can be put? Okay, I will show an example. Suppose this is a heat exchanger. We put a powder onto the top surface. The rotary table is in horizontal plane. It just turns in this way. The rotation speed is minimum and nobody turns it like this. Okay, let's check. This is a front view and this is a top view. Okay. If to rotate it without jumps, nobody will, the powder will not disappear anywhere. And another question, please. Wall thickness of these pressed hemispheres. What's the total the wall thickness? If I'm not mistaken, in 2 plates, each 10 millimeters thick. Okay, thank you. The chamber itself turned out to be a very complicated technical task. From one side, the metal consumption shall be minimized. On the other side, this door with the high bending moment, it weighs 600 kilos, and a separate task there was to create the hinges. These hinges. The hinges provide for controlling of all these in all planes. In order that the door to be set, if there is some way or something this could be corrected. Could you please tell the time of the whole soldering cycle? How much time does it take? One product soldering cycle, EBW2023 takes about 1 hour without vacuumizing. Here we would like to save. It's like 1 hour for vacuumizing, 1 hour for soldering, and often it happens so that soldering does not go to the very end, and so in this case the powder is added and the repeated cycle is done. Today we are adjusting the technology, calculating by the vacuum. Maybe we are planning for vacuumizing about 10 minutes, and the soldering cycle shall be selected so that not to surface melt the tubes themselves. Well, if we say that for one large product is 1 hour, for 3 products, 3 hours before lunch we will make 3, and so and after lunch there is another period. Could you please tell? How do you monitor heating? Yes, it's clear the thermocouples and operator checks, but the operators change. Today one, tomorrow another one. So how the monitoring goes of the temperature? you are saying that incomplete soldering. So this is a quite big product, and problems can be large. The software included into the visor, thermal visors supply. Software does not measure temperature. It renders the image in the form of a graph. Here you can see a non-uniformity. How many thermocouples are installed? 1 to 4 can be installed. How many you have? We have 1. The problem is thermocouple is needed to calibrate the thermal visor. So you measure thermal visor. Yes. I can say that in existing situation, existing plant, this is measured by an eye. The operator is very experienced, and the glowing is bright, and he sees. And yes, okay, you're turning us back to 1980s. Yes, no. We are not trying to do this. We are trying to remove weaknesses of the plant. Could I have another question, please? Well, you are the same very plant, which is smart equipment factory, which had some negative experience with OKBM Afrikantov. This factory was participate to OKBM Afrikantov. Yes, we did many participation in many contracts. Did you have the contract with OKBM? Yes, it was. Yes, it's sufficient. Okay, let's see. Mr. Dragunov says it's 1980s. OKBM Afrikantovs, if you have read the terms of reference, they have a similar task, but it's resolved with a minimum heat input. What you have shown us might be quite expensive, comparable to the cost of a car. So why, if there exist already resolved tasks, you do not reproduce them, but you are saying that this is a modern level on the modern base? Now we need to progress are resolving this task in such a way that we are falling into the zone with minimum heat input and the control. The specifics is that what the tube diameter was there. There was possible in that case to solder with a gun accurately each tube separately. You see here, when the pipe is pipe's opening is 1 millimeter, and when they are when they're dense in hundreds, if you will solder each one, it will be just difficult. If you have large ones, yes, it's quite easy to solder each one along the circumference. But here, the advantage is that you can solder several hundreds. And with a big heat exchangers, it has about 1,000 tubes. And if you calculate the length of the weld that you will follow, you will lose the productivity. These are 2 approaches. Your approach, yes, it's quite reasonable, but for each approach there is a certain application. Okay, that is not question to you, but to the technology. If we put a solder uniformly, heat all the tubes, and some part of on the tubes are blocked with the solder, well, nobody does like this. Everything is mastered. A tube protrudes 1.5 to 2 millimeters above the tube sheet, and the solder shall be to the height of 5 millimeters. This is monitored, yet it's allowed in between. It's allowed the gap of between the tube and tube sheet of several millimeters. This is quite accurate work. If there are some flowing drops, there is not a reject. The reject is if the rejective is if there is unsealing. To block a tube, the solder is fine grained, so fine. The grain size is about 50 microns. It will not block a millimeter tube. It's not a lead powder, and for this certain task, it's quite suitable. This technology is quite suitable. The productivity is high. Heat loss is acceptable. It's not that so much. If we're talking about larger tubes, well, what was the tubes in your technology? What was the size of the tubes and how many tubes there were in your technology? The scanning resolution is 1/10. The question is the total length of the line your beam must follow. You have the parameters of the action. You have the rate of the welding, and if we divide one by another, we will see the productivity. What you are telling about is to soldering each one. We can ask some postgraduates to calculate which technology will be the optimum with the certain diameter and the number of the tubes. Dear colleagues, could you please use the microphone? Let's stop these arguments. These are completely different technologies. What you are talking about, the Africant of the situations there is very simple. There was the plant bought, and we participated to its commissioning. And to finalize it, it was mounted, installed, started. But there was a software which was supplied by our colleagues, and it was closed. It was coded, and it was impossible to rewrite this code. And with the Africant, there was agreed that the plants were bought by them, preserved, and afterwards they announced the tender to start these plants, and 2 plants were mounted and commissioned, but there was a closed code, and it was not impossible to record. And we have seen your plants; they are quite workable. Well, yeah, we are discussing about the history. We are just talking about this. We have seen the situation from another side. The 2 plants, I don't know who made them, but these were shown to us and probably shown to Teta. So we gave the price, the adequate price, for the removal of completely the software, removal of all blocks, and we would install our own equipment. And in this way, these very sophisticated terms of reference, which was required, would be implemented. And from Africantov, we were told that no, it's not suitable for us. There is another company, a smart equipment factory, which would add the money the price 5 times lower, would do everything. And we said, okay, yes, we agree. So it passed. It passed some time, not long time. And there was the persons from Africantov with us, and they said, yes, please help us. We were wrong. Well, the plants were not preserved. They are operated, and they were operated in the paradigm we were talking about. And in this way, in the plant that you were showing us, which is at installation, it's not commissioned. I intentionally asked about the customer, and yes, if it's Rosatom, yes, we have big problems, but so when you commission, you would please inform us the next conference about it. Thank you. And to finalize what you have said about Africantov, everything depends on the terms of reference. And we are also not for the first year in the market. When we called them and asked what amount of work is required, this format was told it should be mounted, started. And we did this. But regarding the software, the Africantov people told us later that yes, it was in technical assignment, there was a mistake, and that's why it was a situation. So Alexander, I'm very happy that you started the plant for them, and I'm happy that it works. So let's make maybe tell our customers how to make technical assignments. We have finished the report. Thank you very much. Thank you. The next speaker is Yuri Semyonov, Institute of Nuclear Physics. He will provide 2 reports.
Dear colleagues, you see the theme of my topic and also the team. So measurement of the profile of the electron beam, profile size for electron beam welding. So in this process, it's very necessary to know the cross-section of the electron beam, the butt of welding structures being welded, also the position of focus of electron beam relative to the boundary butt surface vacuum. So therefore we decided to give to your attention our measurements in different works, and finally we're improving our changes, and we would like just to highlight them and to present them to you. So the aim is clear. So first of all, we measured the size of the beam of current in the thin tungsten wire, and so the shortcomings were when the beam was crossing the wire. So the drop angle changes from 0 to 90 degrees, and this results in alternating amount of reflected electrons, and so which are decreasing the meter current. So also the low volume of the wire proportional to the square of its diameter and diameter of cross section of electron beam, which is heated up under the beam at small levels, layers of the beam current to the temperature sufficient for the thermal emission. In other work, we had the plate with cross-like slits, and we rimmed the beam in the center of the axis. So the trajectory of the rimming of the beam coincided with the area of crossing of these slits. And so also the plate was quite for a long time under the beam. So therefore the measured current was limited by about 10 milliamperes heating of the meter to higher temperatures, and only after that the considerable thermal emission current appears. Then we took the tantalum plate and we made 5 parallel slits, 0.6 millimeters width, and so also we placed a Faraday cylinder and we measured the charge current. Taking into account this experience, we modernized the measurement system. So we placed a protective screen on the Faraday cylinder, which limits the electrons amount. Since the outgoing electrons, so they decrease the pulse. So therefore, we also placed the measurement grid above it, and so there were bigger slits in the protective screen. So therefore, So the amount of leaving reflected electrons leaving the Faraday cylinder, so it was decreasing. Above the measurement grid, we put the protective screen with the increased width of slits to 3 millimeters. So if you take a look at the time diagram of the measurement, unfortunately it's not clearly seen here. Here the pulse goes from the electron source. It's like about 1 second. Just after about 2/3 of the impulse beginning, we start rimming the beam and see this picture. The pulse currents from Faraday cylinder passing through the measurement slits. Here you see the photos of the measurement meter. You see you see the protective screen on the Faraday cylinder to decrease the amount of secondary electrons from cylinder. Also you see the measurement grid above it. And so it depends on the current amount. So it's possible just to use two types of measurement grids. On the right, you see the measurement scheme. You see all the screens, all the protective screens, and you see measurement grids here. So you see also the Faraday cylinder with the screen. And then it goes to oscillography. It's time diagram. So you see the graphs of dependence of Faraday cylinder current upon time in relative values for different ratios of measurement slit widths and diameter of beam profile on its base. So you see that the beam, when it passes through the center of the slit, it reaches the maximum value. In the middles, you see that the width of the slit it coincides with the diameter of the beam itself. It goes through the slit and it reaches the target. And on the right scheme, you see the slit is less than the beam diameter. And the amplitude of the circle of the current density of the beam, it's less than the maximum amount in the best case. Therefore, if you change the focusing system, the size of the beam, so the diameter of the beam decreases, and consequently so it gets smaller, and the whole beam coincides with the diameter of the slit. So therefore, it's possible to catch the focus point in the region of the slit. And so in this case, this process, the measurement process, can be computerized, and to measure the peak values of the pulses. So the example, you see the oscillogram, where the width of the measurement slit is more than the width of the beam profile by its base. So measuring the current density. the beam current density, so the size of the slit is bigger. And here another example, when we measure the distribution of the beam itself, of the electron beam itself. So the current is 80 milliamperes and the distance is 5,500 millimeters, and the time, the beam reading time is about 5 milliseconds, microseconds. But the whole process by the slit takes about 5 milliseconds. So here we deal with approximation. Find the beam size, assuming that it's normal beam distribution. Here you see the formula which we used for approximation, and also in the bottom you also see sigma included. Then how it was approximated. So the actual measurement, and with the red is the approximation result. And the diameters of the profile of the beam, maybe not the diameter, distribution of current density of the beam by height is 0.6 millimeters. Just consider that in the results of such approximation we get the error of about 10%. As a result of this work, we increased the measured current in several times. In comparison, when we use the power of 60 kiloelectron volts. And so in this case, we measured it to 80 milliamperes, the current. And so the fact that by width of the measurement slit, the width is less than the diameter of the beam profile, by its base the peak height of the distribution of the current density of the beam increases. Please, questions? Thank you for your report. I have a question. About 10 years ago, English Institute, Weldon Institute, I talked to Colin Ripton. So they proposed the commercial product to measure for similar measurements. So it contained meter, 4 radial slits, powerful Faraday cylinder, and the software which allowed just to make only one turn for measurement. So it was about 60 milliamperes and 60 kilowatts. Yeah, so do you know about this device? I haven't, frankly speaking, I haven't seen this work. Yeah, so then there is no need to continue with the questions. Thank you. So what is the resource of this measurement device? Only to measure it once, 10 times, 100 times. So we measured starting, please use mic. So we measured starting from 1 milliampere to 80 milliamperes. At least we had traces only on the measurement grid, and there were no. So there were more deeper traces on the protective screen, and we measured maybe like several dozens of passes. So we didn't have any experiments, just measuring the resource, how, for which period of time it will be. Do you have any other questions? Thank you for your report. So any measurements in electron beam technologies arise much respect because we understand that it's complicated. And here we already listen to reports so that we are ready, so it's interesting, but we don't have any instrumentation for that. But on the other hand, so during about 10 years, similar experiments have been carried out, and some results were obtained by other researchers. And what was the aim of your work? The aim, as I said, it's very useful to know the location, the position of the focus of the welding beam relative to the boundary of the but it was like a scientific curiosity. Yeah, so we just thought that it would be useful for someone. Thank you. If there are no more questions, let's move on to the next report.
Yes, the next report was done. The next work was done by the big team of authors. It's clear that electron beam welding is very important in all production spheres. So let's say that cost reduction with the increase of mass and weight of the source might be useful. In this case, we placed all the elements of the source into one housing, a monoblock. This reduces the volume, the weight of the material used, and reduces the cost due to non-use of high voltage cables. And so the reduction of the production premises was also interesting for us to present to your attention the more compact version of the source of electron beam for electron beam welding. This is the diagram. On the top, we have the input transformer of 30 kilovolts, and the position 5 is the multiplier with multiplication factor of 6. Position 4 is the screen in which the control electronics for the beam and heating control is located. Below, position 3 is the unit of divider, voltage divider for voltage measuring of the source. The next below the gun and the column. Electron optic column and electron gun are similar to those represented in paper 7, but in our case, it has a high energy of electron beam of up to 120 kilo electron volts. We have designed, manufactured, and tested a compact source of electron beam in the form of monoblock in 3 versions of heating diagram. The first version is laser preheating of cathode from cathode emission side. We received 70 milliamperes. The second version is transfer of power supply of electronics of beam control and cathode heating through separation isolation condensers. And the third one with the transfer through the version with the laser preheating in our work showed itself quite reliably in operation. Adjustment and stabilization of cathode current was through control of the laser beam power, and we received the electron current of the source up to 70 milliamperes with the energy of 90 kiloelectron volts. The second version with the transfer through isolation capacitors did not work reliably during the tests. Isolation capacitors were broken down often in the modes not exceeding the operating parameters. After the breakdowns, the physical properties of them changed and they started to work as varistors. So when the capacitors with the high engineering data appear in the market, we will proceed our work. The more interesting version is with the transfer of power supply through two serially connected isolation toroidal transformers. Well, this is the diagram of this transformer. One moment. Here, magnetic line of its transformer is the ring of amorphous iron onto which two coils are wound. The coils are similar and wound into wires. Voltage of a wire installation of each coil of each 30 kilovolts. In this way, the primary and secondary coils can be separated 60 kilovolts. Two serially connected transformers allow separation of the potentials of primary and secondary coils 120 kilovolts. In such a way, electrical strength is ensured through high voltage insulation of the wires of the transformer. Okay, this is shown here. This transformer we placed in the block in the unit of voltage divider. The system ensured reliable transfer of power up to 300 watt for heating and power supply of cathode-related electronics. Cathode heating current up to 95 amperes and the source current of 100 milliamperes with energy of 90 electron volts was obtained, and the measured width of beam profile at its half height distance of 550 millimeters was maximum 0.9 millimeters. If we talk about mathematical processing, this is 9.6 millimeter. High voltage part of the source was implemented as combination of relatively low voltage transformer, as I've shown you before, and voltage multiply based on the two 6-fold multiply of voltage for the secondary coils of power transformer. It allowed to reduce the size of the structure to improve quality and stability of output voltage. Fast response of the source into control signals allowed to avoid damage of welded components in the course of welding. Here is the comparative table of the investigation results. So for standard arrangement and in monoblock in our case, electron energy for standard is 60, for our project is 120. Compared in the first case, beam power is 30, in our case 12 kilowatt. From this table we can see that if to account the ratio of energy is 2, it is known that with increase of accelerating voltage, the volume and weight of the source will increase in proportion to the space. To the cubic and the space to the square of this ratio. This impresses me much, I should say. What else can I say? This arrangement, as we told before, with this arrangement, electron beam welding can be used for welding space shifts of low Earth orbit, and this arrangement can be useful in these kinds of works, since it will have better weight and size, and it will be it will be cheaper to deliver it to the orbit of electron beam welding plant. Okay, thank you very much for your attention. Please, questions, dear colleagues? Could you please tell us, is it possible to see it in reality and see and where your mana block is operated? And is it possible to look at it or maybe at pictures? Could you please use the microphone? I have the pictures at my flash media. It should be inserted into the computer. If there are no questions, let's thank our speaker. Thank you very much. And before going to coffee break, we will have another speaker, Hariton Kozyrev from Moscow Power Engineering Institute, and the topic is combined structures steel to titanium obtaining through electron beam additive manufacturing with the use of intermediate layers of copper and niobium. Good afternoon, dear participants of the conference. This report is the continuation of what we heard before from Mr. Yegor, but the difference is that we used intermediate layers of copper and niobium. As we have told before, that the intermediate layers are quite widely used to improve interaction of titanium and steel. But he already told that refractory metals are used copper, nickel, and some other metals. But the best results are achieved with the combined use of refractory metal from the side of titanium alloy and copper from the side of steel. In this work, we used, as already told, niobium and copper. Copper was chosen before because it does not form pass intermediate composition, both in interaction with steel and in interaction with refractory materials. From refractory materials, we chose niobium because of two reasons. Compared to tantalum, it has a lower melting point, and this allows to improve the quality of the deposited bed formation. And as compared to vanadium, it has a lower range of concentration at which brittle omega phase is formed. Here we can add also that in the literature observed, describing the issues of production substructures, omega phase was not observed, but with the use of vanadium intermediate layers, there exist the papers marking the formation of undesired phase. While the aim was to investigate the peculiarities of forming the bimetal structures titanium to steel with the use of wire additive technologies through intermediate layers of niobium and copper. The specimens were made through serial depositing of copper onto titanium and niobium onto copper. All this was done on the electronic beam plant with the accelerating voltage of 60 kilovolts. They were made several specimens, different in the quantity of deposited niobium layers. For all specimens, its characteristic stepwise change of titanium content in niobium layer, and this is proven. And also a stepwise character of hardness change and different pickling rate of the received layers. Maximum hardness is marked near the fusion line. In this area, the micro hardness is within 270 units by Vickers. The structure of deposited layer is different. In the first layer, we can see formation of dendrite structure with apparent segregation of titanium at the periphery of the crystals. The second layer shows formation of lower level left picture. Shows formation of polygonal large aqueous grains. And in the third layer, the structure can be characterized as especially large grain, and with the size of more than 1 millimeter. In the increased hardness area, it was observed the formation of hardening structures, and it can also be said that this area has a lower pickling rate as compared to other areas. A depositing of copper onto niobium with the different melting points. The niobium layer is surface melting is minimum or absent. So the transition area does not is within 10 microns. Copper is large grain, and on the hardness distribution, we see uniform distribution with a hardness of about 50 units. But with a closer investigation in the specimens in which 3 niobium layers were deposited and titanium content in the upper layer was at about 7%, we can see intercrystalline penetration of copper. In the copper having 6 layers of deposited niobium, no penetration of copper is observed. The content of titanium was below 0.1%, but due to high conductivity of the titanium, the drops flew onto the side surface. So within short time in the niobium, the intercrystalline penetration throughout the width of the specimen was formed. It can be separated several zones. Chemistry of this is given in the tables. It is seen that titanium content near the flowing rate exceeds the content in the niobium grain surrounding this, and this can prove high diffusion rate of the titanium near the boundaries. And on the basis of the content, the most probable is formation of intermetallides in the copper to titanium system and eutectics of this. Since penetration of the copper we attributed to the content of titanium, we made investigation on several specimens in which titanium content in upper niobium layer was different. So we established several factors of influencing penetration. This is, first of all, titanium content. The most active penetration happens with the content of 13 to 20% of titanium. If titanium content is over 25% in the upper layer, intermetallide layer is formed, preventing intercrystalline penetration. Here it was formed in the zone. And titanium content lowering down below 5% also decreases intercrystalline penetration. The second factor was the overheating degree of niobium surface. With overheating till surface melting, also intercrystalline penetration occurs, but here it is limited to the size of 1 grain. Depositing of low carbon steel onto copper. The main problem is different melting point, big difference in the melting points, and also high conductivity of copper. The result was surface melting and active mixing with the steel. In several specimens, steel penetrated up to niobium layer. Due to mixing, the copper content in the deposited steel was different, quite strongly different. In the lower layer, the content is about 43%. In the upper level is 0.3%. The structure is also different. The first layer is mechanical mixture of copper, solid solutions based on copper and iron. The second layer was formation of hardening structures and precipitation of copper-based phase. With the increase of quantity of copper, would increase the deformation of free copper increases. Hardness distribution shows apparent area of it shows formation of hardening structures with dispersed phase. Tensile tests were made on 4 specimens. In this case, with specimens number 1 and 2 had the lower surface melting degree of niobium layers compared to specimens number 3 and 4. As you can see, 3 out of 4 specimens showed tensile strength at the level of use of copper interlayer, and specimen number 3 probably had defects in formation, and that resulted in such. So let's pay attention to specimen number 4. It's non-characteristic. Probably partial fracture was on the copper and partial on the niobium. In 3 out of 4 specimens, fracture goes along the area of mechanical mixture of copper and dendrites. Probably the difference in the linear expansion coefficient, conditioned formation of fracture in this area. You can see the conclusions on this slide. Generally, it can be marked that use of such interlayers of copper and niobium allows reaching tensile strength of copper interlayer in such structures. And so we didn't observe metallurgical problems in this case, but there exist technological problems because it must be selected the mode allowing to minimize the melting degree and mixing of the materials. That's all. Thank you very much, dear colleagues. Any questions? Could you please tell us? It's all clear, except one thing. Why in this structure copper was used? We had the option to use either vanadium or nickel, and we saw from the point of view that that copper does not form excessive phases, and we hoped to reach the result. I mean the strength characteristics, not by the temperature of melting. Yes, from the technological point of view, it's not the best material. And the second option to avoid all this, we can take the soldering plant and just to solder with copper. So the question will be resolved. The layer of copper, well, if you solder with copper, so there won't be any mixing at all. Another question? Could you please tell? Total 4 specimens, one different from one another, was you only had. At the moment, we only tension tested only these 4. As already told, as we have already told, we prepared the specimens but did not have enough time to test these. But at the moment, we have statistics only for these 4 specimens. So the work is at the initial stage, and this is what we have now. Any other questions? No questions. Thank you very much. Let's thank our speaker, and we have a coffee break till
inviting Igor Osipov, a research production company, Tomsk Electronic Technologies, TETA. And the topic of his report is import substitution in the area of electron beam welding. I'll just a bit correct the moderator, but so it's the report made by Saturn. It was supposed to be done by Mr. Polikov, but unfortunately he was not able to come, and he asked me to make this presentation instead of him. But for me, it's principally important that to understand that this work is carried out in ODK Saturn and for them, and we are just standing by. So it's a simple history, as just I told you about this yesterday. So ODK Saturn, for them it was very popular to buy Stegerwald plants. Before, it was kind of ideology in the structure of the company, and so Saturn was not an exception. So they had the plant case 880 by Stegerwald from Germany. A good plant, and it operated well. In March this year, Alexei called me and said, I have only 7 cathodes left, please help me. And it was a ridiculous thing, so actually it was necessary to the software in this plant based on just, German logics. So we used our, so say, Russian approach just to connect. So it was a traditional approach. So there were imported cathodes. So they could be produced not only in Germany but by other companies. But you see the characteristics here. And Saturn even has the detailed chemistry of these cathodes, but you should understand that the main composition of the cathode is tungsten. All the rest is just to define the properties. The first step for us was to repeat the geometry. So we used tantalum instead of tungsten, and we just had the same geometry, but after installation, so it produced an error indicating that it's a bad cathode and I'm not going to work. It should be replaced for a good one. And at that time, so only 3 good cathodes were left. And if we look the operation manual to this plant, you see extracts below. So it's in Russian, you can read it, it's possible to understand, but unfortunately we can't understand what to do with this, so it's very complicated to check all this electrical cabinet, and yeah. So then we came up with the idea to somehow substitute. So this German plant indicates is it the correct cathode or not, but it's not supposed to be very talented, that it cannot touch or smell the cathode, so we can measure only the resistance because it's an electrical circuit. So we started comparing our cathodes with their cathodes from the point of resistance, and we came across another problem. So normal experimentator is not going to take detailed measurements just after 0, and actually everything starts after the 4th digit after 0. So therefore, yeah, we don't have such an equipment to measure such fine resistance, thousands of ohm. So we found such meter at Saturn. And our electronic guys, so they opened the manual, so they just assembled the bridge scheme of measurement. So they measured the resistance, so they selected the required cathodes. So these are just the pictures showing the cathode unit, the replacement. On the right, it's the original one, B, and A, it's ours. Our cathode has a rectangular shape of stamping. It's easier for us from the technological point. It's more complicated to make a round stamp, so, and actually we don't see much benefit from using the square ones. So then we see this scheme, so made in Saturn. In Saturn, all these depositions. So for them, it was important, the first stage, just to replace the cathode and just to revamp the operation of the plant, and also they have all the technological processes. It's very complicated to change the technological process, so therefore it's necessary to follow them. So it was normal, maybe simple work from the point of those dealing with the electron beam welding. So they just made the weld, so they checked, tested, measured everything, and made the conclusion. So the conclusion is given here. So and actually the essence is that the technological modes are the same, so the depositional penetration are the same. And so today they purchased around 100 cathodes from us, so they are operating with them, and so they just accumulating statistics. And there is also the positive side. So first, that the plant is in operation mode, so it produces products. So only the service life of this is a negative side. So you see the operation and the service life. So the difference is in 3 times. So we have like 7 hours in the average, and the German ones were 21 hours. So Germans, they used the tungsten alloy. We used just the tantalum foil. So from our stock, so it was just only the trial version. But from the operational side, so first of all, with these 7 hours of operation, they are within the operational cycle for 1 week. So including the replacement of cathodes, and actually it's not influencing, practically it's not influencing the operational rhythm. So, but yeah, so they have a short service life, but they're cheap and it doesn't matter. So the same work was done for Kazan in engine production plant. So they also has Steigerwald plants. So we produced the trial batch of cathodes from tungsten. So 2 points. So first of all, the service life, and then the tungsten which is used, and we understand that not everything is not stamped well with tungsten, and annealing is involved. So if you manage with all these things, so I'll tell you about the success in about 3 years. So this is it. So now questions. So seems everything is clear. So everything, thank you. Actually, it was interesting to hear such productional tasks. But talking about the chemistry, did you try to evaluate the chemistry? How pure was tungsten? Maybe just to try the chemistry. Once again, I want to repeat, so this is the work by Saturn. So this chemistry was assessed by them, they checked it, it's no need to evaluate it. It's Germans are Germans, so they just provide you with a batch of cathodes with the paper inside, and this is the composition, and nothing can be done. But another story is that we looked at it and we said, Germans are good guys, but actually when we took a look, so we just didn't know what to do. But talking about this emission stuff, as far as I know, So these halftones with alloying with some or another element produces an atomic layer on the surface, and therefore it maybe improves the emission. So probably you could think to work and interesting to work in this direction. Yeah, I can agree with you, but the only thing what differs me from your scientists work in the budgetary educational or a scientific educational institution, and I, a commercial guy, work in a private company, and our aim is just to gain profit. Yeah, it's curious, but we are loaded with contracts, and we took tungsten. Just applicable, yeah. So tungsten is available in the market. It's sold by several domestic companies, and we do believe it will be available in future. And even if it doesn't have the same characteristics, it's not so principal. So actually, for the company, it's necessary to know just the penetration depth, and afterwards to have the service life, just for them to work within 1 week. And when the week is over, so they just throw them away, and this is it. And maybe it's also interesting that it was a curious function in this German plant. So during the evaporation, its resistance increases. And why do they use these thousands? So when the cathode resistance increases and it gets thin, so it can be burnt off, and they just block the machine. It's necessary to replace it. Please look through the manual through the operational manual. Thank you. Another question. From experience, practical experience, some time ago I worked in the Titan research institution, so we produced such plants by ourselves. It was called Luch 1, Luch 2, maybe you've heard about them. And what tungsten do you use, or you want to use? Pure tungsten? In your experiments, do you use pure tungsten? Or it's a secret? Please, often in Kyrgyzstan, yeah, in some exotic language from your experience. Yeah, actually it's an ally. There is no pure tungsten in nature. Yeah, it exists, but it's not. It's produced from powders. Yeah, but actually it's an ally which we use. There is such a VR20. It's tungsten plus rhenium. Maybe it was VR18. And rhenium is added for plasticity. And it's good when we used this alloy in our plants. It's plastic, it's very ductile, and the wire is bent well. 0.2 millimeters, yeah, and actually they have longer service life. So yeah, so thank you for your advice. Probably we'll check it, we test it. Thank you. If no more questions, so yeah, thank you for your report. And the next is the online presentation, as far as I understand. Alexei Sherbakov, Moscow Power Engineering Institute. Good day, dear colleagues. Do you hear me? So we see you and we hear you. So please start your presentation. So please start. Okay, so next slide, please. So this is the topic of our report. So it's dedicated of the verification of the methods of diagnostics of electron beams. It was developed a few years ago at our institute, and it was the task as we set for us. So just to evaluate connected with the reflection and re-reflection of electrons. So in my report, I would like to tell you in more detail about this method of diagnostics, and also I will describe the technique which we used, accuracy or error in measurements, and also I will tell you about the results which we got. So the first, what I'm going to talk to you, so there are a lot of different methods of diagnostics of electron beams. So they can be divided into contact and contactless. In contact one, so the beam is impacting the solids, or maybe gaseous or plasma, and our method is contact. And one of the varieties of its so-called direct or probe methods, in which different static or mobile meters are used. Some of them absorb the electron flow, like Faraday cylinder, or they just cut part of this flow. So here you see the most popular diagnostics methods. Many of them are commercialized, so there are certain patterns. And the first one, the probe method, it's the method of rotating probe. Methods also based on Faraday cylinders and other moving diaphragms or plates. In the center you see the meter developed in the USA for Siaki company, where the beam moves in spiral in such slits. A 3D profile afterwards of the current distribution is built. So we also proposed our method, our option of scanning the profile, the beam profile, which is indicated here on this slide. So the essence of this method can be explained by this picture. So the main difference of our methods from many well-known ones is based on using slit diaphragms, is in that the upper diaphragm is placed in those parts of the beam where the density of the flow of the heat flow is not high. So there is no melting there. So it moves discretely up to the width of the slit and stops. So the second diaphragm, which is in the plane where the diagnostics go on, it moves when the top diagram stops. So it starts operating, and the probe characteristics are taken. And for this, at the bottom you can see the meter, like Faraday cylinder. It's indicated as a plate here, but actually it's a cylinder which is isolated from the body, connected through the zone. So you see the protection, gas discharge, and filter, and also we use pre-accelerators, pre-boosters, and finally we obtain the signal to the computer, send it to the computer, it's processed, and afterwards we get 3D distribution of the beam profile. Next slide. Here you see one of the modification of the meter, and so PhD thesis was defended based on this. So the methods of processing the measurement results were proposed. It's a static meter. So the plates are not movable, but the meter moves on the trajectory like meander trajectory. So the meter is installed inside the vacuum chamber and moves against the beam. It can move in Z plane, and the scanning goes on in Y plane. So here, with the help of this method, we obtained such kind of profiles of the current density at different distances from the focusing point of the beam. So it's above the plane, it's unfocused area. So here, when we are approaching the plane, so the beam focuses, And so the distribution changes. In the plane of the best focusing, we found out that approximately the diameter of the beam is 0.6 millimeters, and below the focusing plane. Next slide, please. We see the increase in the shear, in the current density in the peripheral area of the beam. So these are the preliminary results obtained at that time. And we actually set up such a question: is it possible that the measurements produce deteriorations? So like reflection of electrons inside the slits or between the diaphragms of the meter, and probably this process can result in some distorted value registered, and we decided to check it. And to check it, next slide, we used, though it may be strange, we used the mathematical modeling method, but the methods used in electronic microscopy, we created 3D geometrical model of the meter and set up the initial distribution of coordinates of electrons as a module of electron as a large particle in this model. Next slide, please. And then we used the known Monte Carlo methods of continuous breaking of electrons, and also the calculation of trajectory parameters of the section of elastic dissipation. So maybe it's one of the simple models, but also the most frequently used one to evaluate the backscattering of electrons and the energy, the absorption energy of the beam. So this model takes into consideration, collects all the losses, and in this case evaluates the breaking losses, and also the geometrical parameters of the trajectory, the length of the trajectory, and also body angles of dissipation, of scattering. So they are found by the probability function, by Monte Carlo methods with the current parameters of electron and its current energy. So it's kind of a lottery of random values, but the most probable values are the length of the move of the free move of the electron, and other parameters like screening parameters and so on, which are found by energy and so on. Next slide, please. So here you see the parameters of the model we used. So in the model we had two materials, tungsten and copper. So you see all the parameters given here. Next slide. So the electron beam in this case was set not by a Gaussian distribution, but even distribution, and actually it was necessary because we had to find out what's going on in the process of beam reaching the collector, the diaphragm, our diaphragm. Next slide, please. So here, in case if the reflection and the re-reflection of electrons doesn't influence our measurements, the first to be done is that the signal which we register should be similar to meander, but with some inclination area at the beginning of beam crossing the slit. And we got this graph, and it got with this help of this stochastic model. Next slide, please. To prove the adequacy of the measurement methods, we also used the analytical model, which was developed based on geometrical characteristics of the beam and emitter, not taking into account the electron reflection. So which means that the electrons, so they just drop inside, go through the slit and got into the collector. And we used these two models for our calculation. So we used the geometrical model, but the reflection is not considered. Next slide, please. So the condition used in this model is that the electron, if it passes through this rectangular slit formed by two diaphragms, so it inputs the signal to the collector. If not, then not. Next slide. And with the help of this model, we got such a characteristic. It has small deviations from the number of trajectories, number of particles passing through the slit, but maybe we didn't have enough particles, only 10,000, due to the discretization peculiarities, because electrons were separated in discrete way by space. Next slide, please. But in general, comparing the both curves, it indicates that the character is similar, and based on the share of energy energy received by the collector, the divergence was very small, very insufficient in percent. That is, it's 1.36% versus 1.2%. So we can even assume that this small divergence deviation is just connected with some specificity of the model and discretization that we use numerical methods and so on. Some errors and so on. Next slide. And in conclusion, we made such preliminary conclusion that reflection and re-reflection of electrons taking place in collector slits, and re-reflection is between both diaphragms. It doesn't sufficiently distorting influence, doesn't have distorting influence on the registered parameters distribution of current density of electrons. So practically this is what I wanted to tell you. Thank you for your attention. Thank you, Alexei. Questions, please? So first of all, I would like thank you to such a simple and clear report, and you don't feel yourself as an idiot when listening to it. So everything is simple and clear. Then I'm going just to ask you a question. Maybe it's not directly connected with the topic of your report, but anyway, I feel that you have the experience in this field, and I want to ask you a fundamental question. Very often people who operate the distribution of density and power and so on, and dealing with these distributions, which seems to Gaussian ones, but they actually very much different. People speak about the beam diameter. It's a fundamental question. What is the beam diameter? So, for example, there is an approach when we say that the beam diameter is measured on the level of 0.7. So, but it's in radio engineering. It doesn't deal with physics. And one of the great scientists said that it's the diameter of the beam is the area where 90% and 99% of the current passes through it. And what is your opinion? I also don't have one or single opinion, because there are discussable papers what is supposed to be the beam diameter in Weldon literature, but if you take the normal distribution and calculate what is the power share inside the dispersion and what will be absorbed in between the, so it's like 63 and 2%. But in the majority of books, it's indicated that the beam diameter is the diameter inside of which 90% of energy is evolved. So therefore, I don't have just, let's say, the universal answer to this. But anyway, so this method was prepared by us just to see what shape our beam has and what are the characteristics near the focal plane. So therefore, it's like this. Thank you. Other questions? Good day. Thank you again for your report. Please tell us, and how do we correlate, if I understand correctly, so the work is done to find the beam distribution, how they correlate the diameter of the window in your work with the diameter of the beam, and in the method which you propose, so what is the ratio, and do you consider this, take it into account? Yeah, so it's a very interesting question, and of course, the lower slit, in my opinion, is supposed to be by order less than the cross section of cross the dimension of the beam. It's supposed to be 50 or 100 micrometers, but the upper slit is supposed to be bigger because it's unfocused. So it's approximately like this correlation, but discretity will be defined by the movement. So it's not possible just to to find the point where the collector is. It's done by servo motor or servo drive, and we know where it is located. It's maybe like this. Thank you. Other questions? One more question. Alexei, in your modeled beam, the shape of this beam was cylindrical or conical? And the trajectory against the axis, could it influence the result? So it's an interesting question. So it was a cylindrical model, and the convergence angle was 0. All electrons, so they were flying in parallel. I'm talking about the second geometrical method. Yes, of course. If you have another geometry, beam geometry, then it won't be used if you have another geometry of the beam. Thank you. Other questions? Thank you for understanding the report, and I have such a question. So in what power range do you work? So actually we tested this meter, so there was no any cooling, liquid cooling, only heat conductivity cooling during radiation, and the ultimate power was 2.2 kilowatts, so a bit damaged it, and all the cycle was 30-something seconds. It can be done faster, but it depends on the drive which is used, how it's adjusted, and so on. But to increase the power, it's necessary to apply liquid cooling. Yeah, but it will complicate your experiment because But thank you for your reply. Thank you. Any other questions? If there are no questions, we say thank you to Alexei, to the speaker, and as far as I got, the next report is also online report. Alexander Nikharoshev, Moscow Power Engineer Institute. Yes, we hear you. It's necessary to turn on video. Will it just prevent? Oh, yeah. So we see a presentation. So please go ahead. Yeah, so actually I'm ready. Good day, dear colleagues. So first of all, I would like to say that I'm very happy to be present at such a conference and to speak at this conference. First of all, I would like to say thank you to the previous speakers for their interesting reports, especially the colleagues who presented their new developments in electron beam welding. I am the PhD student of the Department of Metal Technology, and I would like to present my topic, my report, my presentation. The topic is on the slide, and we will talk about the investigation of the influence of technological parameters. As you can see from the reports. So recently we have the intensive development of technologies in electron beam welding, formation. So this technology is used in production of components and parts and analytical equipment, aerospace, machine building, and so on. Among the main methods of additive formation with the help of electron beam, so the following can be indicated. So the parts using the raw material wire as the material used for this. And so when we just trying to improve these technologies, it's necessary to implement the synthesis of shape formation, of obtaining the material of the required chemistry directly at the impact position of the beam. So for this, several wires can be used, made of different materials. And in this weld of melt, so we can get the material in situ just in the process of creating the part. But as the practice indicated, so this requires just to adjust the parameters to have stable shape formation. And because of this, we formulated the aim of this research, and for this we set up such tasks to a few words. I would like to say a few words about the experimental stand, and this stand was designed based on the electron beam complex with vacuum chamber for 1 cubic meter and fixed electron guide in 15 kilowatts. And just to calculate the good location of all the elements, so we designed a few scientific schemes, and as we use welding mechanisms and also wire feeding mechanisms with electric drives, so they were also equipped with 2 feeding rollers to provide or to avoid sliding of the wire and to improve the quality of the final product of the part to be produced. And also we adapted the plant for computer control, and also we used the stopping blocks for feeding the wire. And after the stand was assembled, so we had a trial welding. It was carried out at our department, and so this deposition which was produced, it demonstrated that the sand worked in a good manner. So the next stage of this experimental weldings was the feeding of the second wire. And so the wires were just fed at the beginning and the end of the welding bath. And so the inclination angle was 60 degrees, and the welding speed was 100 millimeters per minute. And so the frequency and the amplitude are also indicated here. So it was ring 25 Hertz and 8 millimeters was the amplitude. So when the beam current was used 20 milliamperes, so it was melting too much at the contact point, and there was also some splitting of some drops of the added material as it's indicated on the slide. As a result, so the substrate and the bead used, so we reached the required results. And at the bottom you can see that if you move to the bottom to the bottom part, so these inclusions are decreased, and the alternate structure is indicated here. It is connected with the influence of the substrate influence. Also, this experiment demonstrated the positioning of the end pipes with the degree of 25 degrees. So it requires just to feed the wires from them up to 25 millimeters, and so in this case it's very difficult for the beam to reach both wires because they are supplied in coils and they are deformed when they are fed. So the second deposition was made with the angle decrease up to 45 degrees. So we adjusted the modes. So the speed was decreased to 8 millimeters per second. The feeding speed and the welding speed was increased up to 125 millimeters. And so this location of the end pieces resulted in the stable formation of the initial bead, and also this good mixing of all the materials to be deposited. And it was the quenching structure used, and which was seen, and also, and so this structure is similar to the deposited level produced by the second bead. And also we see some small local austenitic zone. And when we tried just the second layer, the second bead, so it was the wave-like deposition. It's connected with the fact that actually the end tube position or angle was changed just to get into the first bead. But if you take the secondary deposition, so actually the structure was without much difference in structure, but the viability of the second bead also, it was produced in the austenitic zone. So this experiment demonstrated that the heights of the end tubes in comparison with the first experiment, so it was quite big one. And due to this experiment, we got a very important parameter which was adjusted in detail. So it's the height of the end tubes till the first roller, the first bead. So the third deposition was carried out with practically the same modes as the previous one. So there was testing of welding the next layer. So initially the bead was welded on the substrate to 22 millimeters, and with this test, we realized that it's the normal height, and so the bead height was 0.8 millimeters, and for the next one it was the same height was used. So this deposition, the first two layers, so they were uniform. And the wire was used in a stable way, but when we deposited next bead, so the same, so the wall was deposited in a wave-like manner, and so after that we saw the 4 zones, quenching structure. So in this sample, we also measure the chemical composition in four places, in substrate and first and second and third beads. And as from the results, we see that the chemistry changes in all of them. So we see small quantities of chromium and nickel in the first one. And so it means that the metal of substrate is actively used, and then it decreases practically twice. So we see that in the third layer there is a deposition with the participation of only molten materials and without the substrate metal. And also from this experiment we made the conclusion that to equalize further layers after the second one, it's necessary to decrease the beam current just to avoid excessive overheating of metal, because the previous levels are already heated. So therefore, it's necessary just to decrease the speed, because the heating was going on also through the layers and the substrate. Next slide. So in this slide, you see all the main conclusions in our work and during our research, and based on these conclusions and certain parameters of deposition, we made another series of depositions, and finally we constructed the wall from 62 layers, and you can see it. If it's interesting, the modes, we use the inclination angle 45 degrees, and so afterwards the end tubes were just raised up to the height of the previous layer, and so we started with 15 milliamperes up to 9, and then after that it was the same current. And this is it. And yeah, thank you for your attention. I'm ready to answer your questions. Thank you. Please, your questions. Any questions? So thank you very much for your report. And as far as I understand, we have the final report.
Mr. Ivan Chulkov. Good evening, dear colleagues. My report is dedicated to experimental determination of absolute thermoelectric coefficient of structural alloys and pure metals. In electron beam welding of heterogeneous materials, there exists such a problem that with heterogeneous materials, thermal EMF is generates, which is conditioned by the material properties. In welding, the thermal EMF forms in a closed circuit a thermoelectric current, which induces the magnetic field. In this magnetic field, an electron beam starts deflection from straight trajectory. And from the result of this, in penetration of big thicknesses, above 40 millimeters, the sufficient is deflection. And this results into incomplete penetration in the weld. Consequently, one moment, there exist various methods to prevent these defects. The most widely spread is compensation of deflection using the different systems of different additional equipment, and in this case we do not require to know the parameters of the magnetic field which is formed with thermoelectric currents, but we must know displacement of the beam from the joint and inclination angle of the trajectory to the joint plane. These parameters are usually experimentally obtained and complicated and another method is preliminary correction of the beam position, and this can be done due to deflection of deflecting system of standard electron beam. But these parameters for deflection shall be calculated mathematically in a model, and here one must know to receive the good parameters, the absolute thermoelectric coefficients, the properties of structural materials being welded. And now there exists the problem that the properties of structural materials, thermoelectric properties, are very poorly known in point of view of physics. For the electron beam welding, they are interesting. There was assembled a bench to measure thermoelectric properties on the basis of integral method. This bench consists of programmable muffle furnace, thermoelectric sensor based on DAC, and the data acquisition system based on another DAC to acquire information about temperature and thermal EMF of the welded materials. The measurement procedure was as follows. For integral method, there was manufactured thermocouples which consisted of the material with well-known properties. It was chromel in this case, and the test material which were under consideration. This thermocouple, the test thermocouple was placed into the furnace, and to control temperature being measured in the close vicinity, there was placed a type K thermocouple, chromel-alumel, to measure directly the temperature in the course of heating. And these thermocouples were very close to one another, hot junctions of the thermocouples, maybe 5 millimeters away from one another. And they had the same geometry. And they were shielded also by ceramic, let's say insulators, in order to heating parameters in the course of heating would be the same for both thermocouples in order not to get divergence in temperature. Heating was done from 100 to 1100 degrees with a rate maximum of 9.1 degrees per minute. Then there was recorded, the data was recorded by the recording system for the test temperature and the temperature by the sensors. Then the data obtained was differentiated in order to obtain this thermoelectric coefficient, because this is integral method and we needed differentiating. Now it was done by Newtonian numeric method on irregular grid, because the spacing was irregular. And afterwards, there was calculated the absolute thermoelectric coefficient for the material, because the absolute thermoelectric coefficient for chromel was known. There were received the following results. For example, for commercially pure nickel, NP1 and NP2, interesting here is that these materials have quite high thermoelectric coefficient, which is negative, and they have extremum. The extremum is, according to our data, in around 370, 380 degrees centigrade, and it's close to the temperature, to the Curie temperature in this material. Also, we tested other materials, titanium alloys, and tantalum to niobium. Pure metals, tantalum and niobium, they had changing sign of thermoelectric coefficient near around 1 and 2. This is 1 and 2, and titanium alloys, they have the change of the sign around the 0.3. So the 0.3 is near the polymorphous transformation. Other materials based on nickel, nickel alloys. For these are characteristics that, for example, an ethanol NT1 has a quite high positive thermoelectric coefficient, but this is very different from other nickel alloys. Okay, and also the alloys based on iron, they have quite different behavior of thermoelectric coefficient change, depending on temperature. And if we consider, for example, the alloy 09G2S, which also polymorphously transforms. So in the zones 1 and 2, at the beginning and the end of polymorphous transformation, there is a the behavior of change of this coefficient. We see local extremums. The conclusions are, in our work, we mastered the procedure of measuring the thermoelectric properties of the structural materials, which can be used further for mathematical modeling of thermoelectric thermo-EMF in calculation of welding of heterogeneous materials, and also received the opportunity to compensate deflection of the beam without the full-scale experiments, but by mathematical modeling. And also we found dependence, and also we found dependence of phase transitions of the first and second kind on thermoelectric coefficient, on temperature. Also, so this can help determine other properties of the materials. This is all. Thank you very much for your attention. Dear colleagues, please questions. Thank you very much for your report. Thank you for the interest to the topic. Yes, EMF results in mistakes. So I didn't clearly understand that tracking system can compensate, as you said at the beginning of the report. This is not very clear for me. This system, tracking system, is usually set by the upper part of the joint. If you coincide the upper part, the thermal EMF inside will result in some mistakes. It might be some uncertainty here. There should have been written that the systems of different equipment, they are used in different approaches. They allow to compensate in the process of the work of the electron beam welding. They allow to compensate the deflection. You didn't tell. Could you please say what systems are used? Additionally, the side magnetic field compensating the magnetic field from thermoelectric currents. This can be used. This is an additional equipment, some non-standard solutions, we should say. Okay, thank you. Other questions, please? Any other questions? No questions. We will thank our speaker. This was our last speaker for today. We thank all the speakers, and I will give floor for the final conclusion to Mr. Dragunov and Mr. Zelyov. Dear colleagues, good evening. Yes, I think it's evening now. 2 days of the conference just flew. We had very interesting reports, and I personally liked this very much. I think that we'll keep this practice for strict selection of the reports for the conference about the electron beam processing. And this, I think, will be right, because in this audience, we have a narrow specialists, I should say, the colleagues who are engaged only in electron beam processing. I express my gratitude to the organizers, to all the organizers. Thank you all very much. I will thank all the participants. And now, according to our tradition, we always say if we need conclusion or not. From the past years, from the experience of the past years, it turns out that this conclusion does not go anywhere and nobody needs it. So I think that we won't do any conclusion, and we won't send it to any organizations and to any ministry, and also not to Sportloto. So I think that we all had great pleasure. We all found the additional knowledge and additional experience, and I hope that our audience will expand in future owing to our sponsors, NITI Progress and TETA Ltd, because these they keep the constant systemic work on attracting the customers for electron beam equipment and electron beam technologies consequently. So I think we will skip the conclusion, and owing to our 2 large companies, I think that we will expand our audience. What else I would add? That we've discussed with our colleagues and came to the opinion that the presentations that we have seen today can be sent by request to the persons present here, if a speaker is against, you can take out your presentation from the colleagues and you will keep it, and other presentations can be by request sent to those interested if you give your contact. I think so. Here we have agreed, and thank you all very much for your participation, for your joint participation. And Mr. Alexander will add something. I will argue a little. I think that one conclusion from the conference we shall do, judging by the quantity of the reports dedicated to additive technologies, the next conference shall be named Electron Beam Additive. Well, and some other, we should formulate in some nice way. Yes, we thought about this and we are just keep thinking on it. So maybe we should change the name of the conference. But you see, in this case, we will be lost, and this will again be the first one. So we have a deep sense here. Electron beam welding, it's like it was always at the first place, and we always talk about this process. And the second, and the heading is related technologies. So related technologies also deal with the electron beam processing, thermal heat treatment, welding, additive manufacturing. All this relates to related technologies. I think that's enough. But I think additive will be a very popular name. Well, let's think about it. Maybe we will just we should change something. Let's think about it. As we have agreed, I think that the next venue will be Tomsk. The venue for the next conference will be Tomsk, and the organization will be our joint work. Two institutes, Perm Polytechnical, Moscow Power Engineering Institutes. So we take the responsibility for organizing the process, and from our large companies producing the equipment, we would require that the audience be full. Those equipment customers be present in the audience. Any objections from Teta? And in the big audience? Mr. Grigori will confirm this. Yes. So in order not to look like we didn't participate, yes, it's our long-term agreement that in order to understand, in order to keep this conference always fresh and new, each time we gather together, yes, as the receiving party today would fill it with its own energy, I should say, and with gratitude again. We are the competitors. We joke about it all the time, but we are very thankful. We are very thankful to NITI Progress and in person to Mr. Alexander that this is just perfect and very excellent to have a conference in a domestic surrounding at the manufacturing company. So we are also interested in all this. Yes. So for all of you and for all who you can invite, we invite to Tomsk. This will be in a year. We will do our best to make the conference interesting. I can still joke like as an option. We should call it additive technologies and related technologies, including welding. Yes, we can reform, but well, in fact, additive technologies are not very ripe at the moment, so the reports are mostly of scientific nature. And from practical use, the welding technologies are ripe or mature, they dominate, and they take about, in the volume of electron beam, they take about maybe 99% as compared to the additive technologies. So well, I wouldn't obstacle the welding topic. So I have the proposal I don't know if we will catch the Bulgarian partners. They call it electron beam technologies. Maybe we will call it in the same way. We have 2 years in front of us, so let's think. Dear colleagues, the not only 3 persons standing on the floor and the beautiful lady here. Anyone can take the microphone and tell whatever you want. Yes. Now we are discussing what happened in these 2 days. Okay, let me again thank all of you, thank all the guests of the conference. I was very glad to see you. With some persons I got acquainted for the first time. With some of them we are good partners, and with some of them we have friends. So we're living and breathing in this topic. And for us, it was very important to see all you here. Thank you, just huge thanks to all of you. Anyone wants to add something? I would like to make a small remark. Despite that, if someone tells that I don't want about the presentations, if someone doesn't want to send it, the video archive in YouTube can be seen on the website in a week, anytime, week, 2 weeks, a year. So please, you can write to the reporter, and your questions will be sent to the reporter. Well, I would like to thank once again the hosts. I want to tell that we struggled for the right to hold the conference 2025 in our city, but we lost to the Tomsk. I hope that we will have another chance, and next time the Commission will be more agreeable to our proposal. For this, I take the liability in 2025 to show more results and reports from us. I thank all the participants. I think the level grows up with each conference. Each time the reports are more and more interesting. And this topic, this subject, is the subject we do not lose to the competitors, to our global competitors. And this is all owing to all of you. Thank you. Well, dear colleagues, let's finish and leave this audience. And the restaurant for the party is not far from here. It will take 15 to 20 minutes. And all of us together, we will go this road. Who wishes can go on foot. Who doesn't wish, he can use tram or a taxi, whichever. Thank you. Все, нас уже отключили. Ура! Они, ну это тут
Я
вот,
понимаю, да, но просто...
ну типа там аддитивные никак не выделены.
Нет, про аддитивные, да, но я же сказал, чувак, что тут как бы аддитивные, это ничего.
Ну типа смежные, да.
Просто к тому, что международные, то, что у них название меняется, она же уже станет другая.
Так вот он и говорит, что это же так будет первое.
Да,
Вот. Да. Вау.